Okay, it's a pleasure to introduce Roberto Fernández, who will talk about high temperature cluster expansion for quantum systems.
Okay, thanks, Paulo. So I'm very happy to be back in the IME after many years. I was for 4 years, I was a visiting professor here in the 90s, at the end of the 90s. But I was part of the probability group. So the condition to be a professor here in the probability group is that you have a forbidden word, which is quantum. We cannot talk about quantum. So now I have the opportunity to take revenge. I like to advertise here, in a sense, the technique of cluster expansion, which many of people in the audience know, which is the kind of the quintessential perturbative argument used in physics. And the point is that it's a love-hate relationship. There are people that don't like cluster expansion at all and try to avoid it like the pest. And there are people that everything is written in terms of cluster expansion and you don't understand a thing of what they are doing. So I like to take an intermediate position and try to introduce you to the principles on which the cluster expansion is built and to convince you that it's convenient because there is a big part of the cluster expansion formalism that is well known and you can take it right from the shelf and you don't have to worry anymore. Now the cluster expansion was introduced long ago in the 40s to explain the virial expansion, which is the way to deal with real fluids. Okay? So you have the equation of the ideal gas, which was the end of the 19th century, but you needed to go beyond that when you started discovering the superfluidity and things like that. And then there was the proposal of the virial expansion, which is an expansion of the pressure in terms of the density. And it was initially a phenomenological expansion. The coefficients were measured from experiments. But, and then in order to explain it from first principles, from a microscopic model, Maia proposed the cluster expansion as an auxiliary device. But the cluster expansion took a life of its own, and it was adopted in the 60s by people in quantum field theory and in statistical mechanics for perturbative arguments and even multiscale arguments. So you won't see any relation with the virial expansion. There is a further chapter how you go from cluster to virial, which we're not going to discuss here. Now, all these applications were classical, because even in quantum field theory, you take Euclidean point of view, and this becomes a classical system. And there was no standard high temperature expansion for quantum systems. And that's what I would like to discuss now. Quantum systems were treated as spin systems using an alternative technique, which goes under the name of Kilbush-Salzburg equations, which is a complicated way of approaching it, but it's easier to set up, though the mathematics is more involved. It's a infinite system of equations relating the correlations, and then you have to use some argument to prove that there is a fixed point, and this fixed point has analyticity. And it's less efficient than having the expansion. That's the point. So what we did with my former student and now colleague João is to take the ideas of the Gibbs-Salzburg and use it to develop a full-fledged cluster expansion, and now the results are better, as you expected, and you have more control, and that's what I would like to discuss today. So let me introduce you to the notion of cluster expansion. So cluster expansion is a power expansion of the logarithm of the free energy or the pressure, depending on which point of view you take for your ensemble. So this is the log of a partition function, which has to be written in the grand canonical form. I'm going to show it, show the expression. Now, this is an expansion in terms of a variable which are called fugacities, In fact, they should be called activities, as I learned later. But anyway, it's an efficient variable. It's an effective parameter. It's not really completely physical. And it's the only parameter in the most versions of the cluster expansion. And you are dealing, in principle, this grand canonical function corresponds to a class of objects, which are called polymers, interacting by hardcore. That's the traditional approach. There are generalizations. They could have a two-body interaction, but I'm not going to get into that. And hardcore means that there is some rule that says when two particles cannot coexist. Okay? Typically, for the quantum, is overlapping. Two of our polymers cannot overlap, but it could be more general than that. Not overlap and also have some conditions on some extra attribute like colors and things like that. So that's the basic setup that I will try to discuss. Now, what do you have to do to use the cluster expansion? So you have to deal, you have a problem. For instance, you want to develop things in a way that becomes summable at high temperature. This is the high temperature expansion. Or the opposite, that becomes summable at low temperature. This is kind of the Piers argument, and the objects are contours. So you have to find the right variables, the right objects, on which, so that you can write the issue you are dealing with in the form of a grand canonical partition function with exclusion. Once you do that, so then you are in business. Once you do, that's the hard part, to write things in this way. This is where creativity contributes. After that, there is a theory that is already existing, and even you can say now you use the cluster expansion full period. This is something that Dobrushin didn't like, and he says that people use the word cluster expansion as a magical spell that solves everything. But indeed it does, and that's what I want to convince you. So these are three typical applications, but there are others. There were coloring problems that dealt with this. There are many, many applications that, as long as you can write things in this way, you can work with the cluster expansion. Now I'm going to concentrate on a high temperature expansion for quantum systems here, just to illustrate the difference between classical and quantum. So what do you do with this cluster expansion once you have this expansion for the log? Well, you have to determine the region of convergence. That's the point, because once you have convergence, then you have analyticity, because this is uniform and absolute convergence, and then you can differentiate the expansion, and you get everything else you want from the system. Typically, you get correlations, you get density, all as a power expansion in this fugacity. But as you have full control, and you are going to work in regimes where the fugacity is small, you can already use the terms, the first few terms, to see what is going on. So you have full control. Okay, so, and then you can do more general expectations by using some linear combinations. Observables have to be local, but that's usually the case. Okay, now once you have convergence, then you have a bunch of traditional consequences. If you are dealing with a statistical mechanical system, you have a lack of phase transition in the strongest possible sense, which is analyticity of the free energy or the pressure. This is a very strong form of lack of phase transition, which goes beyond mere uniqueness of the state. Okay, and there are situations in which you keep uniqueness, but you lose analyticity. There are some subtle singularities, which are called Griffith singularities, in which the free energy remains infinitely differentiable, but no longer analytic. The derivatives grow with the factorial of the order in a way that is not summable. Okay, so this is not a thermodynamic transition. This is not something you observe. There's not going to be a change in the behavior, but mathematically there is a problem there. So you cannot expect in general that the cluster expansion will give you uniqueness all the way to the critical temperature. That's maybe too much. When you have Griffith singularities, okay, there, if you start having them, you lose analyticity, but you continue with smoothness, you see? And this is a very subtle way. So that's what is an obstruction to reach the critical temperature with the cluster expansion. So you stop before that, but for a mathematical reason at least. I don't know whether maybe there are some physical consequences, but they are not so obvious. You don't see it in the macroscopic behavior. You have to do maybe some study of a microscopic level. And more than that, you have absolute control of everything you want to ask. Okay? Because it's a series expansion, and you see the role of the different parameters. You really understand everything. Of course, in a regime of a small fugacity, which is, in our case, with high temperature. But then you use another expansion for low temperature, and you understand in both. And the idea is that basically, you can go through the phase diagram and study each region around the points where you know, using some suitable form of cluster expansion. That's kind of a meta approximation, meta theorem. Okay. So mathematically you work, there are two steps. The first step, that's where you really have to work, is what I call gas expansion, which also called polymer expansion, which is write the object you want to deal with as a gram canonical partition function of some suitable objects, which you construct out of the expansion. And I'm gonna, well, you will see how general they can get in the quantum case. So these objects could be called molecules, polymers, whatever. And the only interaction that in this version of the cluster expansion they're going to allow is hardcore. So there is some relation, incompatibility relation, that tells you if these two things are incompatible, they cannot coexist. They cannot be present at the same time. And we can deal it with this in a very general way. Again, it's not the most general framework. You can do it with other not hard two-body interaction, but most of the time you end up writing as a hardcore interaction. That's most of the applications that I know. And that's where more precise results are available. And once you wrote like this, that's it. You know the expression of the series for the log. It's already well known. The combinatorics is well known. And you know conditions for convergence. And there are several conditions that were evolving in time till we arrived to what we think is the best available condition now. Okay? And there was a lot of effort here, because that's what makes the whole argument rigorous. Okay? Where do you converge? So just for your information, there are different methods that try to avoid using the cluster expansion, because people really try to avoid it. Especially the American tradition is, if you use cluster expansion, you are not clever enough. You have to come with some shortcut, elegant arguments. The problem with these elegant arguments is first that they are ad hoc, they are suited to certain model, and they are not robust. You perturb the model and you lose them. You see? So I am naive and I use a cluster expansion. Okay, but one of the guys that didn't want to know cluster expansion, didn't want to use was Dobruchin. Unfortunately, because the Russians are brutal people. They really like big expansion and they work hard. But Dobruchin didn't like this attitude of invoking the cluster expansion all over the place and not saying anything else. So what he produced, which I'm not going to discuss that, but this will be a nice topic for a mini course, is a 5-line proof of the convergence of the cluster expansion by producing an inductive hypothesis on what happens when you add an additional polymer to your expansion. So it produces a very well tuned up, and you prove that if this is satisfied, then if you have analyticity for n polymers, you have analyticity for n plus 1, and that's it. So he called it the no cluster expansion approach. And it was surprising because the criterion he computed was better than all the available criterion that used the cluster expansion. The proof was extreme, very clever. And there is another approach. If you want to improve it, you cannot. You try to do, let's go better, because you know that there are better. Yeah, the happy when you have yes, no phase transition. The happy families, yeah. So it's very hard to improve, and you see inductive arguments, they are not revealing. You don't know what is going on. You are lucky. You got the argument, but what is happening? What is making the expansion converge? The point is that anyway, a posteriori, if you want control, you have to use the cluster expansion, knowing that with this argument converges. Okay? So this was a big question. Why the nice methods that we knew were improved by the brushing without really using the cluster expansion? Okay, it's a big question that we had. There is another, the alternative approach that is even older than all the summability approaches that are used nowadays, which is this Groupoids, which is a very nice, very elegant system of equations relating correlations. They are all coupled, and then you prove this is a linear, so you have a matrix, and you have to prove that there is introducing some artificial, if you want, Banach structure, you prove that there is there is a transformation that is with norm less than 1, and you have a conversion to a fixed point by iterating, and this fixed point has analyticity and everything. Okay. So then again, a posteriori gives you the cluster expansion. So we compare. There is a paper in which we compare this approach with the cluster expansion approach, and we prove that this approach, in fact, happens to be equivalent to the brushing, the condition. But if you have the cluster expansion and you really see what is going on, you can go better. You can do better. Okay. So, so this is the point that the situation we wanted to improve. In classical mechanics, most of the time you were dealing with expansions of systems with two-body interactions that then you rewrite as hardcore. Or some exceptions, but it has to be a very dominant two-body interaction. For multi-body, people use Groupoids, okay? But they were less precise. So at the very least, we wanted a multi-body high-temperature expansion, full-fledged, without avoiding it. And in quantum mechanics is, except for the low-temperature expansion, in which I also have been involved, so where we can consider quantum contours, so quantum version of the Peierls argument, which is more involved because you have to put one more dimension and the geometry is much more involved. Except for that, people use the Groupoids equation. Okay? And certainly not many multi-body, not multi-body at all. So this is the situation we wanted to improve with my student at the time. And what we managed to do is we obtain a multi-body cluster expansion for high temperature that works for quantum and therefore for classical, because the setup can be put in a similar basis, and I'm going to describe it. And what you need is the condition that the interaction has to be exponentially summable in the number of bodies. But this is not a loss of generality, because already for quantum systems, you know that without this condition, you cannot prove the existence of the dynamic for KMS, for the Hamiltonian. So this is the very least you need for quantum systems. And for classical systems, there are examples by Dobrushin and Martirosyan that shows that if you have interaction, that you can cook up interactions that are not exponentially summable in the number of bodies, that do not have analyticity at high temperature. So in a sense, this is optimal. You cannot go better than this if you want to be so general. Okay? For particular models, you can do better, but on the generality we want to discuss, no. Okay, so when you want to include cluster expansion in the quantum mechanical setup, you have to afford working with operators that do not commute, instead of with functions that commute and you can group and factorize and things like that. So you have to learn to live without commutativity. And we use the ideas of Park, but Park used it to develop a Groupoids approach. But the ideas were there. If he had pushed it long enough, strong enough, he would have gotten our expansion many years before now. Okay, so let me describe the general setup of a cluster expansion approach. So you have some objects that we call polymers. If the Bruce wanted to call it animals, you can call it molecules. So they are usually complex objects. They are formed by many things, many groups of smaller or more elementary objects. You will see an example in quantum mechanics. And I'm going to use the letter gamma for the polymers. And you have an incompatibility constraint, okay, which being incompatible, I'm going to use it with the bar, which if you go to graph theoretical approach is kind of the opposite, because in graph theory, being incompatible means the being linked, so people use that one. But I'm taking the traditional physical approach, so incompatibility, this means that they cannot coexist, they cannot be present at the same time. And that's all. So for simplicity, I'm going to assume that each polymer is incompatible with itself, otherwise you have to sum up, resum the activities, and it doesn't give you anything. And then you have a family of activities. That's the only weights you have, which more or less you can say this gives you the convenience of having this polymer present or not. So that's all. The constraint, the objects, and the activities. A very simple system. And then with that, you have to write, this is the grand canonical partition function. So you sum over all possible families of polymers, as big as you want. There is the n factorial, and these are the activities. So this is from another paper, so it should be rho. But I use Z, which is the traditional way in chemistry. And you need, so the only condition is they have to be present, so they are weighted by the activities, and they have to be compatible between themselves. So here, notice the 1 over n factorial, because here I'm considering the ordered sum. You could remove it and put here brackets, and these are sets, because each polymer is incompatible with itself. But, so these gamma 1, gamma n are all different. But it's good to keep it like that, because first of all, because then the sum factorizes into partial sums, or sums over each, and also because when you go to the log, you lose this identity that you can remove this and put bracket, and you have to stick to this form. So this is one of the things that you learn painfully when you are a student, okay? You can get confused with that. So, but the real object you're after is the log of that. So the compatibility is, here, these things are, these are supposed to be numbers, for the time being, commuting things. So the compatibility, every pair in here has to be compatible. If there is a pair that is not compatible, it doesn't count. That's all. That's the whole interaction. That's what a hardcore interaction is. But you're interested in the log, okay? For many reasons. The log of the partition function is the generates all the correlations. You take derivatives with respect to this, to set gamma 1, you get the probability that gamma 1 be present, okay? So you have full control once you have the log. Or you can do probability weights. Here I'm missing a factor in which you weight each particular configuration. The probability that a certain configuration of polymers be present is, well, they have to be present, they have to be compatible. What I'm missing here is the sum over all the polymers that are compatible with them. There is another partition function here that I forgot, which corresponds to lambda minus these polymers, and then you normalize. So this is an honest probability distribution. And you have this ratio of grand canonical partition functions, which becomes, in fact, the object that, the most revealing object. Okay, and you can, by integration of these ratios, you can get that, or by differentiation, you get to the ratio. And the type of questions you want, so in here, there is this lambda here. This lambda means that I'm talking initially with a finite family of polymers, very big, usually polymers within a certain volume gamma, but it's finite. So this sum is not an issue. This is summable, no problem. When you go to the log, it's no longer. Because you take the log, then you become a full Fourier series all the way to infinity. But these two objects are well defined always. But you are interested in taking lambda to infinity. Okay? And you can take it at this level divided by lambda, or at this level. You cannot take it at this level. Yes?
But you divide by volume or don't care?
Well, in principle, here for that, in principle you wouldn't care, because I would use that to compute this type of ratios, and there the volume disappears. Okay? But yeah, one of the questions is, what happens with this log when lambda grows? And the proof is that it doesn't grow faster than the volume. So 1 over volume this divided by the volume of lambda, the number of quantum, should converge to something, which is the pressure or the free energy of the infinite volume, the thermodynamic limit of the system. Okay, so this is here.
You said that the compatibility relation is not reflexive. It's transitive.
And it's not transitive, but it's reflexive. No, it's not transitive, definitely not. But it's reflexive. It's overlapping. Just imagine overlapping of sets. So it's a relation. I mean, it's a very basic relation. Just to call it. Okay, so you go the limit of this. You have to prove that this limit exists, and it becomes analytic in the fugacities. So it's a in a polydisk. You would like to study these measures, these ratios of partition function for finite lambda, because you want to have very often finite volume corrections, and this allows you to do that. And then also the asymptotic behavior of this is to be an omega lambda of this. This should converge to a limit measure that is well defined. So this is the type of things you are worried about in the mathematical terms, and then you can deduce many more because of the convergence of the different expansions. And here is the part you don't need to know. This is telling you, if you have your grand canonical partition function written as hardcore, as I wrote it before, when you take the log, you get this, which is an expression that has the same form, with the same things, but the weights are different. Before, the weights are just the product of indicator functions of compatibility. These weights, in a sense, are completely the opposite. You have to consider they have to be here. They have to be non-compatible. They are called clusters. So you see, what you have to do is the following: you take gamma 1, gamma n, and you draw the graph of incompatibility. And this graph, which I denoted that way, has to be connected. So really, this form and this is a cluster, a family of polymers that cannot be disconnected with compatibility. They are all intrinsically incompatible. They form an incompatible set. For instance, this n could be copies of gamma 1, because each one is incompatible with this. So there is a huge number of things you have to sum. And worse than that, when you take this graph of incompatibility, the weight is you sum over all the possible subgraphs of it, connected and spanning, visiting all the points. And for each of these subgraphs, you put this extremely corrosive factor. It's a -1 for each bond, each link. So this is, in general, for n large, a huge sum, many terms, but they cancel each other. And they have to be incompatible. If you can divide them into two compatible subfamilies, this is 0. So that's the point. When you go to log, you pass to incompatibility. This is the edges, the set of edges of this graph G. So for each link, for each pair of incompatible, it's not that every pair is incompatible, but it has to be sufficient incompatibility to create a connected graph. For each pair of incompatible here, you put a -1. Or for each subgraph. One of the subgraphs is the full graph, but there are many more. So you have a huge number of terms with alternating signs. And you better take care of these cancellations or this explodes. Okay? So this is well known, and the proof is not very complicated. And what is nice, we know how to deal with these terms. So really, you don't need to worry about that. That's the nice part. All the complicated combinatories, which is contained in this, plus dealing with these terms, is done. You take it and you use it. That's why it is a very convenient approach, I say. Okay? So here is the most general convergence criterion that we obtain. And we could explain why Dobruschin was better than Kotevsky price and what people were done before, and why we could improve Dobruschin. And this is something I will take to my grave. I improved Dobruschin. So it's very simple. So the point is the following: you can describe these terms. You can write it in terms of trees. Okay, so this bunch of trees with a changing number of children that satisfy conditions between the different children. The conditions are more complicated, but and that's the thing we discovered with Aldo. The most important condition is that the children had to be compatible between themselves. They had to be incompatible with the root, but they had to be compatible between themselves. And this is something that nobody used before. Dobruschin used the fact, Kotevsky price used nothing, and they gave some nice bond. Dobruschin used the fact that the children had to be different without realizing, and that's why he improved what people did before. If you use the fact that they have to be more than different, they have to be compatible, then you get the best criterion you have now. Now, how do you prove sums of positive terms labeled by trees? You do it inductively. Basically, what you do, you take the first generation, okay? Here you have the row that you want, and here you put some weights mu. And if you show that this is less or equal than putting just a mu, you can iterate this sum. And you see that as you get more and more trees, you always are less than mu. And as this is a positive sum, you are proving that the sum is bounded, converges. That's it. It's very simple. People worried about and put Banach structure. Banach has nothing to do with this. It's a positive series. You just have to. So, and this is an if and only if condition. So that's the optimal way to prove the trees. So we can prove we can sum the trees very well. These trees are already a little approximation because we are neglecting other second degree conditions that they are too complicated to consider. So this is what is written here. So this is the first order tree. Here you put a 1 in there, but then you multiply by lambda. I call lambda instead of rho. So this, you see, this is the first generation. So these are all, you take many children, all of them have to be incompatible with the root, but they have to be compatible between themselves. And you put mu at each child, and this is the condition. If you lambda times this is less or equal than mu, you get convergence. You have to find a mu such that this is not 0, and then you define, this gives you the radius of the disk in the y direction. I'm using y instead of gamma, different publications. Okay? So that's the condition. So this is completely known. So once you have your expression for your fugacities, put an upper bound of this expression and then try to find a mu that does that. You have also, depending on the kind of relation of compatibility you have, is the phi you write. Okay? And that's it. So you see, once you have this condition, you have convergence, and you have bounds for these ratios of partition functions and for the log, which gives you the finite volume corrections and in some settings are information that is important. So this is the rules of the game. It's extremely efficient. You have all your effort is to write the partition function in this gas form as a grand canonical partition of object. And there, you really have to be creative. The object could be very weird. Okay, but once you do that, then the next phrase is now we use cluster expansion, full PDF. Because then, okay, you have to do a little calculation to find the optimal mu, some optimization. But usually, in most systems, that's not a big deal. You need some work, but this is elementary. The hard part has been done for you, because there is a control on the cluster expansion itself. Okay, now, in our example of high temperature expansion for quantum and also classical spin systems with multiple interactions. So I'm going to present a framework that works for both classical and quantum, to see that it's the same mathematics. So the point, you have a lattice. This is lattice systems. We have extensions to continuum systems, but for here, for quantum, only for the lattice spin systems. And at each side, there is a space. Depending on the problem you have, is the characteristic of this space. Let me go vague at this point. So the structure of the space depends on whether you are classical or quantum or whatever application you have. And then you have the final products of this space. And the idea is, if you are dealing only with quantum, with classical, you can let lambda go to infinity, because this is a product of measured spaces, and this is well defined. But if you want to include quantum, then this is a product of infinite product of Hilbert spaces, and this could be problem of definition. It's certainly not unique, and you avoid it. You try to avoid it. So I'm going to follow a general framework that also works for quantum, so I'm going to avoid it. And then what is the way to avoid that is to go to observables. And there is where the algebra of observables, where you take the limit, the projective limit. Okay? So you have operators for each final lambda, and you consider this included. So there is a limit in the sense of a limit of algebras, which for our quantum application, this will be final matrices, so they're easy to deal. Okay, so and then the last ingredient, you need a map, a trace, I call it trace, which acts on these operators. And well, and they have to satisfy the trace properties, that they have to be invariant under permutations, cyclic permutations. They have to be linear. This normalization doesn't mean that trace is a probability measure, just normalize it. Continuity with respect, because the space of operators have to have a norm, but they're very simple in our case. And the factorization. The disjoint subsets, the trace factorizes. And with this normalization, that means on the rest is just a 1. Okay, so these are the ingredients, okay? The space, the observables, and the trace. So for classical, the space is a measured space at each side, with some a priori measure. And the operators are just functions, okay? And the trace are just product of these probability measures. For quantum, you take a finite, in the spin case, finite dimensional Hilbert space. Let's take it the same. Then you take boundary operators, these are matrices, and the trace is the normalized trace. Okay? So, but the properties I'm going to use are the properties I listed before, and I don't care whether I'm here or there. The mathematics is going to be the same. So then you have the interactions. So these are a family of operators that are local. Okay, that they depend on a local set of sites. Then the bonds are those operators that are non-zero. There are going to be many that are zero. Not every x has a phi x with non-zero phi x associated. And then you construct the Hamiltonian. Okay, this is, and then once you have the Hamiltonian, you define states, finite volume states, in the usual way. Okay, taking trace A times exponential, and the normalization is the trace of the exponential. So normalization, but this need not be a trace, need not be a probability measure. Okay, this could be complex here and there. So beta is the inverse function. This normalization, you call it partition function, and the log of the partition function is for the sign, you call it the log of the free energy. Now, this formalization involves, this is a free boundary condition, so, or empty boundary conditions. You could add boundary conditions and define the things with boundary condition here. And there is a divorce between the classical and the quantum, because in classical, if you consider boundary conditions that can be treated exactly in the same way, same expansion and everything, there's no problem, then the expansion in particular shows that these limits become independent of the boundary condition. And in classical, you know that these limits for different boundary conditions gives the extremal points of all possible states, so this gives you uniqueness. There is not a general, a comparable theorem in quantum, and that's a question that I keep posing to the KMS people. You don't have an analogous theorem that's saying, okay, you can put, for instance, Simon proposes quantum boundary conditions, so you complete the exterior of lambda here at the level of interaction with a state outside. Okay? And you can deal with these states in these limits, no problem. And you can prove that with the cluster expansion that is independent of this quantum boundary condition. But there is no theorem that tells you that these limits generate all possible KMS states. You may wonder whether, if there are other states that don't show up this way, whether they are physically relevant. But this is another discussion. Okay? Certainly, we cannot claim uniqueness of KMS with the cluster expansion approach. We can only say that it's insensitive to boundary conditions. Okay? For the classical, we get uniqueness. Okay? But you get analyticity of the free energy, so this is already a lack of phase transition. Okay? But this is part of the mystery of KMS that we still have to understand well. Okay, so let me see how do you jump from classical to quantum. And this is a very silly, stupid comment. We realized it after looking hard at what Park was doing. You see, the traditional approach to develop a cluster expansion when you have a classical Hamiltonian is to write. See, I keep repeating. I mean, I had a professor when I was studying at the University of Buenos Aires. The math career at the University of Buenos Aires was set up by Spanish immigrants that came from the Civil War. And one of the professors, Balanzat, repeated very often that mathematics is the art of adding 0 and multiplying by 1. So I'm using one of the versions of the principle here. Okay? And then what you do is, okay, you develop this product and you label the terms of the product by those families in which you choose this, because the other don't show up. Okay, and in here is the product of these things. And then you decompose these families according to being disjoints or not, and you get your grand canonical expansion. Okay? But this step you cannot do in quantum, because you cannot factorize. And that was the instruction to use these techniques. But then you see, when you go here, that if you reassemble this, you get this expansion, this term. And these terms make sense for quantum. And also, you can separate it in disjoint parts, because when they are disjoint in quantum, they commute. So they become a product. So the key was not to stop here, but go all the way here. So what are you really doing? We are using the Möbius transform. That's what you really is acting behind the cluster expansion. Okay? So this first thing is false unless you go all the way to here, and then you can use quantum. So this gave us an idea of what is the universal way to generate a cluster expansion whenever you have a hardcore condition of whatever object you have. So this I'm reviewing the Möbius transform for you. You have two functions, there is a set, finite, and you have a functions of the subsets. And you can write one of the functions as sums of the over subsets of the other, if and only if the other is written this way in terms of the previous one. This is an if and only if, you prove it by induction, it's kind of an elementary game. And that's what is behind all these complicated, seemingly complicated combinatorics. So, because what you want, our f is our initial exponential. And we want to write it like this and then expand it in product. Okay? So what you need is to add the existence of this compatibility relation such that, first of all, which has this property. If you are compatible, the function f factorizes. If my f is e to the minus beta h, this holds for quantum. Whenever two subsets are disjoint, the corresponding Hamiltonians commute. So the exponential of them factorizes. And then you can easily see through the expression that I wrote before that the G inherits this. Then you decompose sets C into connected parts using the compatibility relation. And you decompose each G, in which F is greater than a sum of G over subsets. You decompose each G into its connected components. And here you have an universal cluster expansion. So I have a function F, which has this nice property factorization with respect to some compatibility relation. Then I can automatically write it as a grand partition function. Here I cheated, I wrote it not with the 1 over n factorial ordered, but because I was saying before you decompose into components. You write it like this, as long as these things are defined that way. So this is a universal way of obtaining the cluster expansion. Almost over. But no, I started late.
Okay, so how then?
Plus 10 minutes, okay.
10 minutes is okay. So be patient. So what do I do with the gas, the quantum gas? Then is, as I told you, this is trivially the fact that if you have disjoint sets, the exponential of the Hamiltonians factorizes because the Hamiltonians commute. So here is the expansion at the level of operator. This is an operator. I can write it as operator. I didn't say they have to be numbers, you know. But the fugacities, they have this expansion. So you see this expression. So you see they are polymers. They are formed by families, big complicated things. So the whole rule, so I have this. So the rule of the game, so what I'm going to do, then I'm going to hit it with the trace. And given the factorization property of the trace, the partition function here will become here using partial partition functions, the trace of that. And then, so that's the hard part. Once you have this, you can use the cluster expansion, and then you have to apply the convergence condition, for which you have to find an upper bound to these things. Okay. Okay, so this is the way you write it with the trace in it. So you replace the exponential by the trace of them. Okay, so this is, I already said it. You can continue, etc. So now the problem is to find this bound. Now, if you are classical, this sum, I already said what it is the product of this factor e minus 1 that I had before. So then it's very easy. You bound it by the bounds of the product. And then you see that you have a high temperature situation because when beta goes to 0, this becomes very small. But this is quantum. I don't have that. But you have, nature is good. You have an upper bound like that. This is proven in Park's paper. You can prove it by induction. It's straightforward, but not easy to write. But it's true. Okay? This sum can be bounded by this. This is the fugacity. So this is the same. See? Yeah, here you have a lot of synonyms. Yes. Yeah, that happens when you have many papers, you know, and you take from all of them. Yes. But that's a way to keep the audience awake. So that's where you make the connection, having high temperature with having convergence. And then what you need is to find a bound of, so you bound this, and then you need that this lambda satisfy this condition, convergence condition that I wrote at the very beginning, for some mu that you have to optimize. And the phi is, what you need is that all these different children are incompatible. That means they have to touch, intersect the root. They have to intersect the root. Where is the chalk? So you have to intersect the root, but then themselves, they cannot intersect each other. And this puts a strong limitation on how many you can have. Okay? So this you have to do a little algebra, but it's not more than algebra. This is the mu that maximizes this. Yeah, that I learned it when I was a referee, and I said, what the hell is this? No, yeah. The mu that this is Armax means the mu that maximizes what you have on the right. It's a convenient. Yeah, it's even official because latest has it. So this is official. I mean, that's recognized by the community. So, in fact, when you do that, you can get another, doing some changes, another condition in terms of weight A. So let me not go that because traditionally you write A of x as a constant times the size of x, the size of your set. And the advantage is when you replace there, you have to find only one thing to maximize, which is this constant A. So, but this is kind of a standard for people that have worked in custom expansion. And, well, okay, so anyway, I hear there is some, you have to do some song and dance. And you see that in order to find maximizing mu, you need this condition. And this is where the exponential summability enters. And there is no way, you cannot escape it. But it's there for a physical reason because for KMS to make sense for interaction, okay? And you end up, by using this bond, having this kind of bond, when this is a function that you can write, and then you maximize over A, and then you go numeric. And here is the results, and I think I'm going to end up with this. Our conditions are this less or equal than something like that. It's small, but it's non-zero. And that's one of the points that I also want to get across. You can use this for numerics. Usually cluster expansion is used in a perturbative way and say, there is a beta big enough for which you have analyticity. No, I can say how big it is. Within that you can work. And in some cases it's good to know. So you see that for low dimensions, I improve a lot with over the Kilburg-Sarwood approach of Parker. But as the dimension grows, I kind of converse, we can converse of the same thing. Okay? Now, Simon produces a bond in his book that is much worse than the Parks, which is worse than ours. So there is some improvement in this game, plus all the control that brings the existence of this expansion. Okay? Now, let me end up with a final comment. Why these numbers are so small? Okay, and when you do numerics, I think you could go beyond. Why I lost my chalk?
There.
Ah, okay. And there is a problem. Let me work in the limit of in the set axis, or a set, or I use it rho and you use lambda, fugacities. Huh? And C, yes, thank you. Yes, yeah. You get a very detailed alphabetic knowledge here. The problem is that we are working in polydiscs. We say C less than some constant for each y, polydiscs. Now you can prove that the nearest singularity happens at z equal -1, which is unphysical. Okay? So you have a very low convergence in the physical region because of an unphysical obstruction. And this is telling you that there is a problem on the domain of convergence, the type of domain of convergence that you are using. You are using disks. It's natural for power expansions, and this is what people have been doing all their lives. But it's not natural for physics. So you would need a change of variables for which you get something of this type. And then you start trying to find out, and then, I mean, okay, at some point you stop because you have better things to do with your time. But we have a suspicion. We have a suspicion, which is the variable you have to use. And I think that nature is pointing in this direction. Remember that I talked about the virial expansion. The virial expansion is an expansion of the log of the partition function, but as a function of the density. And the density is basically the first derivative of the log of the partition function. This is the density, okay, which I don't know which letter to use now. Let me use delta. Okay? So if you want to obtain the virial expansion, you have to take the cluster expansion, take the derivative. This is a series, delta in terms of, invert the series, plug it back, and then you get your virial expansion. That's a very beautiful combinatorial exercise. We have a publication on that way. But what we don't have, I you suspect, is that if you expand the pressure in terms of delta, the density, the real physical object, then you get a domain like that. That's what we expect. It's not proven. There are some examples by Sabine Jensen that confirms that, but it's not proven. Okay? So this is something that can be done in the future. And I stop, and I think it's, very good. Okay. I mentioned what? Yes, okay.
Okay, thank you very much for the talk.
Yes. Yeah, so I said, in Griffith singularities, you lose the analyticity of the pressure or the free energy. You lose it. But you don't lose smoothness. So they have, all the derivatives are still finite, exist, but they are not summable. They grow too much with n, with the order of differentiation.
You're not talking about randomness.
Well, it's almost randomness because the Griffith singularities are essential. Yeah. Yeah, so but the randomness could be generated by the local fields of other things. I don't know. It's very complicated to say because so there could be. You see, so there you lose the analyticity, but you don't lose uniqueness. You don't. Everything is smooth, but not as smooth as before. Yeah, the American view, yes. Barry Simon, Michael Eisenman. But the point is, these people, they avoid cluster expansion, but then they develop their own expansion. So, well, that because I learned that this hate to the cluster expansion, I learned in the States with them. And I had to do therapy to recover from that. Yeah. Okay. Yes. Yeah.
You were mentioning the one main issue was the sensitivity of respect to boundary conditions.
Yeah, it's often a main issue. So no, it's like adding extra bonds to your interactions. Besides the bonds that are within, they are the bonds that came out, which are integrated with respect to a state out. So the part that is in, the part not integrated, is an additional contribution to the bonds, which only appears in the boundary. But anyway, they can be treated with the cluster expansion, and the summability condition is enough to deal with all of them. So this becomes basically insensitive to the boundary condition. Okay? Ingos.
This singularity which is not
Physical, yeah.
I did work that trying to escape this singularity, and this work has been done with David Bridges, and it's suspicious also. He claimed that if we go to another expansion, which is one particle reducible, which you can reach by this expansion use the Lagrange transform.
Maybe,
we did that.
So you got a larger.
If we do that for the repulsion, for this incompatibility, only the incompatibility.
So you think you can improve?
Yeah, yes, we can actually, but we didn't see any singularity, other singularity.
There might be some radius of convergence in the expansion.
For simple, very simple model. we did that. And then there is no other singularity. We couldn't see transition which
So-
everybody expect that there
I mean, you expect the cluster expansion to hold only up to a certain temperature. You cannot expect to call
no,
it.
we escaped this singularity doing Lagrange transform.
Well, but then I have to see what you are saying, because you have to see a phase transition one way or another. Otherwise, your result is too good to be true. You know, at some point, you miss analyticity, you miss continuity, I mean, the differentiability of the free energy. Okay, well, then you should tell me, you should send me the reference.
There is this paper of Christoph Tenno. It seems that the criterion is better than you and Aldo, but
Yeah, he did a big mess. It took a long time to be accepted because the combinatorial is horrible.
Yeah, but in the final,
He improves, in some cases, he improves our summability because he considers the things we are neglecting. In order of having something simple, to have only a vertex condition on the tree, we are neglecting second order constraints.
right?
And he is including them by considering pairs of points and single points and things like that. And then you get into a mess. You need to be young to do that.
Okay, but the criterion, you don't know, but he has no example which is better, but interact.
I think he has an improvement on something. Yes, I think so. But it's very painful. It's really very painful. I mean, I wouldn't advise it. And I think he's not really avoiding this problem. I think not. But he's getting better than we do because he considers a little bit more conditions. No?
Right.
No more questions? Thanks.
Break, né? Break.
Welcome back. Now, we will start. The speaker is Inés Armendáriz from the University of Buenos Aires, and she's going to talk about Gaussian random permutations. So please.
Thank you for the invitation. It's great to be back in Sao Paulo, and thank you for coming. And we changed the chair because he's part of the talk. This is joint work. I'm going to be talking about joint work with Paulo here, Paulo Ferrari and Sergio Yuchman, both of them in the Universidad de Buenos Aires and also CONICET, which is the funding agency in Argentina. So let me first very quickly go over the model I will be talking about. So our starting point is this canonical partition function describing the Bose gas in a finite box lambda in d dimensions. Here d is general. So we're looking at the canonical partition for n particles in a finite volume. And then the Hamiltonian is given by the Laplacian, plus some interaction potential. And Feynman in 1953 proposed to, via this representation of the canonical partition function that I'm going to go slowly over. So what you have is 1 over n factorial, then we're adding over all permutations. Then we have some weights. These weights are associated to Brownian bridges. These are Brownian bridges. Starting at the point x and ending at the point y. Now here we have the permutation, so x sigma x going over all possible points. We look at the permutation, we have the Brownian weight, and then we have this exponential factor associated to Feynman-Cox representations for those who are familiar with that, which is encoding the interaction from the potential. So given that we have this canonical partition function, then there is this representation. I mean, Feynman already conjectured that it was possible to study the Bose gas starting from here as a model on permutations here. So we read this as distribution on permutations, which are distributed according to the counting measure in Sn, and point, which are distributed in some fashion, which is absolutely continuous with the Lebesgue measure. So alternatively, instead of studying the Bose gas, we could study this model on permutations and points and permutations of the points defined in such a way. And here we will focus on the easier case when the interaction is equal to 0. So we will consider V equal to 0, and then this reduces. Now we integrate, this is gone. So we integrate here, and we only keep the weights, which are the Brownian weights. The weight to have, here I change notation just to use the canonical notation. Alpha is 1 over 2 beta. Beta was the previous parameter. And here these are the weights for a Brownian path to go from xi to x sigma I in time, well, 1 over 2 beta, right? And this is just a normalization. And this is the total normalization, the partition function we'll get from the model. So this is just a picture by Daniel Woolsey describing what's going on. We fix the points, and then we consider the permutation determined by the trajectories that start at the point, finish at another point, and then we go here, here, and so on. And this determines the permutation on the points. All right, is the model clear? So the conjecture, Feynman's conjecture, was that there was a relation between the fact that the Bose-Einstein model has condensation and the fact that there should appear in this model of permutations that we should see that cycles having macroscopic length, that is length comparable to the total number of particles, n, should appear. So it was conjectured that there was this relationship between the two models, the original model and the new model on permutations. And this was proved much later by Andras Schuto in a series of papers where he showed that, in fact, if there is, first he showed in 1993, he showed that if there is Bose-Einstein condensation, then this model on points and permutations of the points would have macroscopic length cycles, and then in 2002 he proved the converse. And not only that, but he identified the density at which we see this condensation phenomena, at which we see that cycles comparable. I mean, when we consider a typical permutation, these permutations have cycles with size comparable to the total number of particles. And it was precisely this, which is also the density at which there is onset of condensation for the Bose model. So, okay, this is just a factor. And then we get this sum, which is the interesting part here, which is 1 over k to the d over 2. So already here, we notice that if the dimension is 1 or 2, if for dimensions less than 3, then this blows up. So for dimensions 1 and 2, the critical density at which there is onset of condensation is just infinity. So 1 and 2 dimensions do not have condensation. There is condensation when d is greater than or equal to 3. Okay? And okay, so we get the same constant for either model. So we will try to study the model of, we will concentrate on the model of permutations. All right? So now we can look, so this model is a model on permutation points and permutations on the point. So we can look at the marginals. We can look at the marginals on the point. This is called a point process. So if we just sample points and permutations, and then we take the marginal on the points, we get the distribution on points, a point process. And this was studied by Tamura and Ito, taking the thermodynamic limit. As the size of the box, all this, we were taking a distribution on a finite box with a fixed number of particles n. Now we fix n over, we take, so we had n points, and we had a box of size lambda, right? And we take this as n goes to infinity, and the box goes to Rd in any dimension, we will take this to go to a given density rho. And we will focus on the cases for d equal to 1 or 2. Here rho can belong to 0 infinity, no problem. And for d greater than or equal to 3, we see that we have two cases. Rho less than rho c, for which we had an explicit expression, or rho larger than rho c. This will be the subcritical and the critical case, and this will be the supercritical case. So we fix the density, given the density, then we can take the hydrodynamic limit. Let the box go to infinity and let n go to infinity, but keeping this proportion. And in 2006, Tamura and Ito identified the limiting process and showed that this is a permanent point process. We will come back to that. And a little bit later, they identified what happens when rho is larger than rho c. So this is for d greater than or equal to 3. And they showed that, in fact, this is a superposition of 2 point processes. So we have 1 point process, and then we put another one independent of the previous one on top of that, so that the sum of the two densities matches the desired density rho. And in 2008, Natalie Eisenbaum, I also come back to this. If you don't know what the Cox process is, don't worry, I will define it. She showed that these processes, in either case, these processes are Cox processes. So Cox processes are like the next level of difficulty after a point process. Point processes are very simple. Poisson point processes, sorry, are very simple. Cox processes are just Poisson point processes where the density itself is random. But given the density, we recover a Poisson process. So this is the story for the point process. So this is what happens if we take the marginal on the point. Now, let's see what happens if you take the marginals on the permutations. You forget that you integrate over the points, you keep the permutations. And there is a result by Benfato, Cassandro, Merola, and Presutti. Titi is here with us from 2005, where they showed that when we look at the supercritical density, which is an interesting case for if you're searching for microscopic cycles, then there is at this supercritical density, there's a tightness of the rescale macrocycles. And this was refined later by Volker Wetz and Daniel Woolsey, who proved this nice result. So what they do is, first of all, let's call nu rho minus rho c. So this is like the extra density. Rho c was the critical density. We take the leftover density. And then we take the cycles. We look at the cycles. This is on a finite box. So you take the cycles. You order them in decreasing order according to their lengths. And you look at the lengths. You order them in decreasing order, sorry. And then you renormalize by, you know that these are going to be, you hope that if you're in supercritical density, this will be macroscopic. So you renormalize by the total number of particles, which is n, and rho minus rho c. just a normalization, and they showed that this converges to a well-known distribution, which is Poisson-Dirichlet 1. So you probably heard about Poisson-Dirichlet distribution. This is a distribution on partitions of the interval 0, 1. So, and there's a very nice construction, which is called the stick-breaking construction. Probably you have heard about it. All, I don't know. What you do is you take a stick of length 1, you split it, for this particular parameter 1, you split it uniformly. Then, let's say whatever I have on my right hand, I will keep it, and whatever's left, I will split it again. Whatever I keep on my right hand, I will put it aside, and so on and so forth, and I keep doing this. This is a partition supported on infinitely many pieces of the interval. And then you reorder all these pieces, which they didn't come out ordered. So you reorder them and you take the distribution of whatever you got, and this is this. So this is the result from Volker, Betz, and Daniel Woolsey. And it's interesting because it tells us something, that in the thermodynamic limit, not only we know the distribution, but actually we will see infinitely many, infinitely long cycles. So we will see that the macroscopic cycles are growing, but there are infinitely many of them in the limit. So this is, if we look at the marginals, what happens if we look at the marginals. So what we set out to do was try to get already an infinite volume, try to propose. You will see where this comes from. The intuition is clear, actually, why we propose what we propose. But we set out to get a infinite volume spatial random permutation. So a permutation already distributed in infinite volume. And we're looking at the two marginals jointly. We're looking at points and permutations at the same time. And what we will get, what we wanted was that if we look at the points, so we want to construct an object which is points and permutations of these points, such that this point process should be associated to the boson point process, which was previously calculated for the model, for the canonical measure model. So this is the free Bose gas at the right density, and we wanted to do it for all densities and all dimensions. And as a side remark, we got some new proofs of previous results that were already known. Once we know for the point marginals, there were some computations already, such as the fact that they are Cox processes, and we could rework this somehow. And so what we got was that for d less than or equal to 2 or d greater than or equal to 3, but at subcritical densities, then our points, the point process, is the point marginal of a loop ensemble. For those of you who know what it is, this is a loop ensemble. You keep the points, and this is what we get. And I will describe how we build this loop ensemble in a minute. We also showed that this measure we construct is Gibbs for the specifications related to the canonical measure I just introduced, and well, some other remarks that have to do with the distribution of the points. Yeah. The law of the sigma is I will tell you. I mean, sigma will be the loops. You will get, in subcritical, you will get the loops, and in the supercritical, you get the loops plus interlacement. So, but you have to construct it together with the points. I mean, you need both, you build both at the same time. So let's start with the loops. So for the loops, let's go over the definitions. This will be a loop. These brackets indicate that, of course, when you have a loop, you don't care about where you start describing the loop. So these are the loops of 4 points. And it doesn't matter if you start describing it here, 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 or here. So this defines an equivalence relationship, and that's what we mean by this. With the curly brackets, we denote the support of the loop. So if you only care about the points visited by the loop, we will use these curly brackets. So this is a set of points, but here we care about the vector structure, only that we have this equivalence relationship. Is it clear? To forget the origin. So we consider this set D. This will be the set of loops. So what we do is, for fixed k, you consider Rd to the k. This is these guys. You take the quotient with this relationship, and then you take the union over all possible k's. So these are all the loops we will consider, the set of finite loops. Notice that all these are finite, of any given size, but finite. And this was the crucial observation, which is a very simple observation, which was that when we have this, let me go back quickly, here. When we were considering these canonical measures, this factorizes in loops. Because you consider a loop, you see how the points are visited, and when you close the loop, then you can take this factor out and start with the new loops. So
can be self-intersecting.
The fact is, there will not be any self-intersection in this case. I mean, if you're in ZD, things get messier. But here we're working in RD, and we're taking, with respect to, I mean, everything is absolutely continuous with Lebesgue measure, so there will not be any self-intersection. Of course, you could have situations like this, and this is not a problem for us. We don't consider, I mean, the loops actually are the points, so the rest of it is just a picture. But in ZD, it's much more complicated, because then you could have points with multiplicity, and the computations get more complicated. But here, that's not a problem. So just by looking at this, we say, okay, so what you could do is fix k. So consider, we could start modestly and say, okay, we want to distribute loops of length k, so we fix our k. And then we will consider this weight. This is just this weight. This is the natural normalization to take with this weight, the Brownian. This is just the Brownian weights. We're choosing them as absolutely continuous with respect to the Lebesgue measure, so nothing here. Then we put these factors lambda to the k. This is the fugacity Roberto was talking about before. This is what we will this will allow us to play with the density. You will see this lambda will be one-to-one correspondence with the density. So this is just so that we can fix the density of the loops. And then we divide by k, and dividing by k just has to do with the fact that we don't want to fix the origin. So dividing by k is counteracting the fact that we counted the same loop k times according to where we started distributing, where we chose the initial point. So this is what this k here is doing. So we take this candidate for an intensity measure. Whenever you want to define a Poisson process, if you remember Poisson processes, maybe from your basic course of probability, in order to define it, you need a sigma finite intensity measure. So we need to prove that this choice is sigma finite. In some sense, it's a space of loops. So for that, we need, the way to do that is to compute the mean density of, I mean, here I'm adding over k, because here I was distributing this for all k's simultaneously. But in order to make it simple, you could say I want to distribute size k loops, and then I go one by one through all the possible values of k, and I put it all together. It's the same thing. So you could say I distribute the 1 loops, the 2 loops, the 3 loops, the 4 loops, and then just throw it all in. So now I'm focusing on this number here with this alpha. This is just the normalization we had, but this is the important factor here. And this is the density we get for k loops. And as you see, it's parameterized by lambda. And here I have the computation, and maybe we don't want to go over it. This is just a simple computation. Don't read it, but just to persuade you that this is a completely straightforward computation to compute the density of loops of size k, so that to make sure that we have a sigma finite measure, that this measure we are proposing for the loops is good. So once we have this, then, and I should say that this program we're following here, we didn't come up with it. It's a well-known construction that was first introduced for Brownian loops by Lawler and Bernard in 2004. And then for discrete loops, this was developed by Lawler and Trujillo Ferreras in 2007. So we're just adapting it to a particular setup. And so now, provided we have computed this already, we know that we have a good candidate for intensity measure. And what we do is we consider a Poisson process. So we are sampling loops. Our Poisson process is a Poisson process. Our objects are loops, and we are sampling infinitely many loops, but each of these loops are finite with this intensity here. And the LS stands, so this will be the intensity. LS stands for loop sup, and lambda is the parameter we play with for the density. And then mu will stand for the law of this realization of loops. So let me, I don't have a picture here. But what we're doing, so what we will get is a loop sup, meaning we get the gas of loops in RD. And then you may wonder, okay, so what happens here? If you sample all these loops, each of the loops is finite, but you may wonder, well, okay, if I look at a finite region, I'm interested in a finite box, finite volume in RD, how many points do we get? How many loops intersect that? And in fact, by Campbell's formula, it's very easy to see that the Campbell's formula tells you that if you have a Poisson process and you want to add over a function over all the points in your Poisson process, then you can compute the mean of this just by integrating the intensity measure. So if we apply this, I mean, it's an elementary fact from Poisson processes. So we do that, and we apply this to our Poisson process of loops, and then we see that if we fix a volume, a finite volume, then the intensity of points, the number of points in this volume will grow as the volume of this region times the density we had before. And the density is precisely this. So from here we can read the following. Rho will be less than infinity as long as d is less than or equal to 2 and lambda is less than 1, because this blows up when lambda is equal to 1 and d is 1 or 2. Or d is greater than or equal to 3. It's the same computation we had before, but we had a 1 here. And lambda is between 0 and 1. We can go all the way to the radius of convergence because this converges for d greater than or equal to 3. So great, this is great as long as we are happy with dimensions satisfying this. Now, what happens if we want to go above this dimension? What would happen? I mean, we get this critical density again that we had before. And the next question is, what if you want a higher density? What if you're in dimension greater than 3 and you want to achieve a density of points beyond this? So the idea here is very simple. This is for finite loops, go to infinite loops. Instead of, get the rest of the density you get it from infinitely long trajectories, just like that. And again, this was already built for us, so we just needed to apply something which is known, which is interlacements, random interlacements. So random interlacements, maybe you have heard of this, are Poisson processes on bi-infinite trajectories. So our space now is not the space of loops. We will have to, now let's build them. We have to consider doubly infinite trajectories. So this W is trajectories that are defined for all times. So time here is n. And again, we're working with these Poisson increments, Brownian increments. So we'll take trajectories such that the increments are IID normal with the right time scaling. So we're looking, essentially what we're doing is we're sampling a Brownian trajectory. Dimension, remember, is here is greater than or equal to 3. So it's a Brownian trajectory, only that we're sampling it, we're looking at it at fixed time intervals, which have this length, 1/2 alpha. Okay? So they look like this, simply because we're not sampling the whole trajectory, but just we're looking at it at fixed time intervals. And by the fact that, you already get some intuition, by the fact that we're in dimensions greater than or equal to 3, this will be transient. So each of these trajectories will come back to any finite region a finite number of times. So this will be good. And now we have to, okay, this is the candidate. Now, how do we define, again, we're trying to build the Poisson process, so you need to define an intensity. And the standard way, if you have ever studied interlacements, is to consider, if not, forget about what I'm saying, the standard way is to consider the first point. What you do is you first sample this point where the trajectory visits the finite volume. You fix a finite volume. You say, okay, let's start by fixing this box, and let's try to sample a trajectory that visits this box. Many of them won't, but let's sample trajectories that do visit the box. So the first thing to do is to sample this point, the entrance point. The first time the trajectory visits the box. Of course, the trajectory could be doing something like this. It could come, do something here, go out, come back, and eventually leave. So we're sampling the point when it enters for the first time, and the distribution of this point, this measure, this entrance time measure, is called the equilibrium measure. And then what you could do is say, okay, I sample this point according to this measure, and then I take a trajectory going to plus infinity without any restriction with these Brownian increments, and then a trajectory going to negative time, also with the Brownian increments, but I have to condition, since I wanted this to be the first visit to the point, I have to condition on the trajectory not visiting the box. So this is how this is usually built. But for us, it was more convenient to consider an alternative way, which was what we call via debiasing, which essentially what it does, I think that's an S, sorry, there's a typo there. So what you do is you sample a trajectory, no restrictions, just sample your favorite Brownian trajectory, and having fixed the volume, now renormalize the weight by dividing by how many times this trajectory visits the box. So you divide in this case by, say, 4. So, and if you do this, if you consider this alternative measure, this measure which is just sampling a trajectory without restrictions and then reweighting it by dividing by the number of visits to the box, you get exactly, we show that it's the same thing as it's an alternative to the standard way. And this was more convenient for us for computations. All right? So this will be our candidate to replace the intensity we have for the loop. So we want to use this intensity. Of course, this intensity seems very related to the choice of the volume. So you need to choose, you need to show some compatibility conditions. You need to show that if instead of taking one volume, you took a smaller volume, you get the same thing. And okay, you show these conditions so that you show that it's independent of the choice of your finite box. And then again, you need to consider the time shift, because we don't really care about the time parametrization of the trajectory. We're only looking at the trace left by the trajectory. We're looking at traces of objects, not the time parametrization of the object. So we have to take the space of bi-infinite trajectories, modulo this equivalence, which is two trajectories are equivalent if one is the time shift of the other. And then we can show, provided we do all this carefully, that there is unique intensity measure that we will call QRI, Ri for random interlacements, on this space of bi-infinite trajectories modulo this equivalence, such that whenever we restrict to a finite volume, you recover this measure I introduced here. So we're good. And next step, we do the same thing. We want to make sure, because we're trying to produce a point process, so we need a Poisson process, so we need some sigma finiteness of this. So we need to study, let me see this, we need to study the mean density of points determined by this measure here. And I don't have it here, but it turns out that the mean density of points determined by this is 1. So if you do this, you use this measure and you fix a box, you will have exactly density proportional to the volume of the box. It grows with the size of the volume you're considering. So let me remind you that we wanted to produce density rho minus rho c, because we were looking for whatever we needed, the extra. We set out saying, okay, I fix rho c, d greater than or equal to 3, and I want to produce a point process which has density rho c. And I knew I could produce up to rho larger than rho c, sorry. So I want rho larger than rho c. So we knew that we could go all the way up to rho c with the loops. Great. So now we need, there's a leftover mass we need to get of order rho minus rho c. So actually we don't want the interlacements, because interlacements would give us a density 1. So in order to produce the right density, we just multiply this by rho. So we take the intensity we want and multiply it by rho, then this will give us a Poisson process with the right intensity. And that's what we do. And as I said before, this was, here we're following a program introduced by Schnittmann in 2010 for Brownian interlacements with other purposes, but it was more like a percolative properties of this, but it's exactly what we need here. All right, so now that's it. The Gaussian permutation, we say that the Gaussian permutation and density rho will be, this piece here is just the loops, and whenever rho is larger than rho c, then we add an independent copy, an independent process of Gaussian interlacements that we built just as before, at density rho minus rho c. So we get something like this. We get the loops, and we also get the bi-infinite trajectories. Okay? So this is our construction. And now we have to check that this construction does what we want. So in order to check that it does what we want, if you remember, we had the characterization of the Bose point process that had been obtained as a thermodynamic limit. So if we want to check that we have the right point process, we need to look at the point marginal. And to characterize the point marginal, one thing you can do is look at the correlations. You have a point process, study the correlations of the point process. So let me just remind you here, in order to look at the correlations, you need to look at the occupation level. So you take some number of pairwise disjoint sets in RD, and you want to see how many, this NAI of X is just, you take the points determined by all these trajectories, by infinite, whatever. This is Then you take the points, and then you look at how many of these points fall in each of these boxes, and you take the product. And this will be determined, there will be something like this, where what you want to identify is this function phi of x1, xn. So here we're adding over all possible n tuples of points in a1, an, and we want to characterize this kernel. This will describe the correlations, and if these correlations do not grow too fast, this is enough to characterize the point process. Provided you can do this for any n. N has to be in any number of pairwise disjoint sets. Okay, and again, this was well known for the case of the loop soup. This was done by Lejean in 2011. This is a permanental process. This is the permanental process I talked about before. And the kernel, this is given, I will come back to this now in the next slide, will make this clear. This k operator we have here is given by this. So kxy is simply the intensity of all the possible ways you can go from x to y, visiting any number of points in the middle. So it's a sum. This is unfortunate. This k here has nothing to do with that. You're adding over all possible ways of going from a point x to a point y. So you have x, you have y, and you're adding over all possible intermediate points you visited and any number of intermediate points. So you're integrating over all intermediate, what the trajectory could have done in going from x to y. X and y are your target points. That's what k is doing. And here is the relevant picture. So suppose we do it for 3. So you have 3 points, and you want to see how you can manage to fit these 3 points in your point process. So what could happen? One thing that could happen is that the 3 points belong to 3 different cycles. That would be the easiest way. So you have to count, and then so you have to see, okay, how many ways in how many ways you can fit a cycle starting at x and finishing at x. So this is kxx, because the cycle in principle will have any length, and we're adding over all possible lengths. Same for y and z. Another thing you could have is that 2 of these points belong to the same cycle, and the other one is in a different cycle. So this would be these 3 situations, and you have to go through all the possible cases. So you have to thread one cycle starting at x and finishing at x, but then you'd have to make one go start at x, go to y, come back. Okay, here I'm mixing the letters. So y going to z and coming back. This is what this is taking care of. And then you play with y and z and x, and you get these 3 situations. Or finally, you could have to thread one cycle through x, y, and z, and you can do it in 2 directions. So we get this case and this case. And when you count over all these cases, you get this expression here, and it turns out this is the permanent of this matrix. The permanent is like the determinant, but you remove the -1 factors when you look at the expansion of the determinant. So it's just adding over all possible permutations, and that's that. So this is a very nice formula, and we recover these, and this goes for any number of points. So and these don't grow too fast, so this is enough to characterize. I'll come back to this if I have time. This characterizes our point process, so that's nice. We need to do the same thing for the Gaussian interlacements. It's not as nice, but we get a similar picture. Now, if you want to fit 3 points, you could make them belong to different bi-infinite trajectories, or you could have here that the 2 of them share the same trajectory, and then you have to account for the 2 possible directions in which you could go. Trajectories come, you don't care about time parametrization, but you do care about direction, so you could go from here to here, or from here to here, that's the 2, and then the case when the 3 points belong to the same trajectory. And you count over all this, and that's exactly how you get the point correlations. And again, you can control this enough so that this characterizes the point processes. And just by using these, or alternatively, we can compute the Laplace transform, some kind of thing, computation like that, we can show that the point processes that we have for all cases match what Tamura and Ito had computed using thermodynamic limits for the point processes of the canonical measures. All right? So this tells us that we have the right point process. So, okay, that's the first result. We build the point process just by this simple computation, by simple construction. And now we want to show that now go back to the full object. We want to study the points and the permutations. So we want to show that this object, these Gaussian permutations we defined are Gibbs. So for that, well, we start first with the canonical measure. We will consider empty boundary conditions. So empty boundary conditions here mean that we're sampling everything inside the box, like what we were doing for the canonical measure. For the canonical measure, we were just sampling cycles inside the box. And we can do that. Of course, we can do the same thing for the point process, for the point and permutations, for the Gaussian permutations, just sample inside the box. And then we can show that if we sample everything inside a finite volume and we condition on the total number of points, we recover the canonical measures. And we can define also a grand canonical measure, which would be what you do from here if you don't want to fix the number of points. So we introduce the grand canonical measure, and again, we get that this is the right thing to look at, that our construction is the right thing to look at. And so this is nice, first thing. This would be like looking at same picture we have here, but when we have no boundary conditions, when we are sampling just inside the box. And the next thing, we want to consider more general boundary conditions. So we have to prove, to prove this Gibbsianness, we want to show that how you match boundary conditions. So here what we have, just look at the colors, we're sampling whatever is in red, points and the arrows. And the boundary conditions are given by the yellow points that have labels, and the labels have to do with the fact that this point will be mapped inside the box, and this point will be the image of a point inside the box. So we need the labels. What we definitely do not need is anything which is in purple. The purple arrows and points will not influence the distribution of points and arrows in red. So given these boundary conditions, actually, the only thing we need to keep are the yellow points and their labels. And we can show that this is enough. So we get a sort of spatial Markov property showing that this is enough information to sample the red arrows and points. So we prove this, and this very much looks like, and from here, this very much looks like the DLR conditions. Because then we can show that if we define the specification given by the boundary conditions, then this measure will satisfy the DLR condition. So we're really getting a Gibbs measure for the specifications. And well, maybe this is interesting for people in statistical mechanics. Notice that if there's a lambda here, and the specifications come with the lambda, with the parameter lambda, and when lambda is less than 1 in dimensions 1 and 2, or up to 1 if d greater than or equal to 3, then this is the measure, this is Gibbs for the specifications. Now, for supercritical densities, then actually we get infinitely many Gibbs measures. So we consider these specifications, and all these are Gibbs for the same specifications. And the reason we get this is the fact that the density is actually fixed by the boundary conditions. The boundary conditions will tell you how many random interlacements you have crossing the box, and this will fix the density. So everything is fixed by the boundary conditions. That's why we see this coming up. So okay, this was one of our main results, the fact that we constructed the infinite volume, just straight away we constructed the infinite volume permutation. Let me quickly go over this, because I mentioned at the beginning, these point processes we get, these point processes, well, the first thing you notice is that you're sampling everything as a Poisson process, so you might think, okay, everything is a Poisson process, this is great, so the points should be Poisson, and the points are not Poisson, in fact, not as simple as that. That there is some structure, that there is some leftover trace of the fact that they come in loops or in long interlacements. If you do a simulation, I didn't get it here, but you do see the trace of the interlacement. So they are not Poisson. Poisson would be very homogeneous, and they are not. But they are a Cox process. So this is the next good thing. A Cox process is just a Poisson process with a random intensity. So you sample first the intensity, you have two levels of randomness. First you sample the intensity, this is a measure, and then on RD, and then you sample the point process according to this non-negative intensity. And we can describe precisely what the intensity is. The intensity here, in fact, is given by, let me see if I have, no, okay, this is just. So what you have to do to sample the intensity, you have to sample to two centered Gaussian fields. A Gaussian field is just a function that takes at each x, when you sample it's a Gaussian variable with a given correlation. And here the covariance is given if you look at the covariance between the value of this Gaussian field at one point or another, is given by this k lambda. And k lambda, let me remind you, was this kernel we had before, which was adding over all possible ways of going from a point to another with some weights lambda that played with the density. So this is a very explicit object we can compute related to the Brownian increments. And then what you do is you sample 2 independent copies of this and you take the sum of the squares. And by doing this, so this is what this says is that here, this is the function we are looking at. It's random because the Gaussian fields are random themselves. And then you look at the Poisson process having this intensity. And this is exactly the point process we're getting. So having sampled this, we get the Poisson process. Here I have a very simple proof, but I won't bother you with it. It's really simple. I mean, it's just, well, okay, maybe for those of you who are familiar with this, otherwise just ignore me for a minute. You want to describe everything in terms of occupation fields. So you take the occupation field, then you condition on the intensity, because you know that you have a Poisson process with a given intensity, so you're conditioning on the intensity. Once you do this, you use Campbell's formula that I told you about before, which tells you that this expectation inside will just be integral of the intensity. The intensity is W, so you get this. You move the expectation, well, you write this as a double integral, you move the Fubinides, move it inside. Use that these guys are just Gaussian vectors, so you know everything about them. In terms of the covariances, you get this, and you get what you wanted. You get the right, this is the permanent of a 2x2 matrix having the right entries. So in terms of correlations, everything is described, and this is telling you that this is the right object to look at. So this is just the proof that this permanental point process we were looking at is a Cox process. And this is for the subcritical, this is enough for the subcritical, but for the supercritical, we have to look at we had 2 measures. We had to look at the point process of the loops plus the point process determined by the random interlacements, and we had to put them together. And this is a little bit more difficult, but it was done by Natalie Eisenbaum for us, and she proved that you have the superposition actually of 2 point processes. So one of them is like before, this Phi1 and C1 are really like before, centered Gaussian fields with the right covariance, with lambda equal to 1, maximum lambda. And okay, you need to look at the superposition of the 2 point processes as we saw before, but still it's a Cox process. So that's very nice because we have a very nice description of the point processes. This is like the simplest description we can hope for.
The relation between this k lambda xy and this Gaussian random walks, right?
What you're doing is k lambda is exactly all the ways in which you go. It's the Gaussian random walk, exactly. It's like how many ways you go. It's telling you how you go from here to here, putting together. That's what k lambda is, with the lambda factor, just lambda to the k factor, counting how many steps you took. It's precisely that. I don't know if this answers.
So it's the Green's function?
It would be the, yeah. It would be equivalent, yeah. So, yeah, I mean, you can, okay, this is a version for our particular case of this. I mean, for general, if you do this construction in a graph, say, in a finite structure, then you see precisely what you get, and you get the Gaussian fields appearing precisely. I mean, here we get the Gaussian, we have this second randomness because of the continuous structure. So okay, you'd get that the occupation field, if you wanted to compute the occupation field of your process, this would be given by the Gaussian, by the sum of the squares of these Gaussian fields. It's exactly that setup. But here, because everything is continuous, we need to use Campbell's formula, essentially. It's telling you that the expectation, and you need to go through a test function, will be given by this. But it's exactly that result, yes. So, okay, just a side comment. What we get is, well, everything now can be described very easily once we have this formulation. And as I was saying before, this matches previous descriptions for loops and for interlacements in terms of isomorphisms by Lejeune and Snitman. Yeah. So I'll stop here. These are our results so far. And let me just tell you some problems. I mean, one first thing that you might want to do, I mean, this is work by other people. One thing you might want to do is that all our results depending on these thermodynamic limits for the point processes. So you might say, okay, why don't we just compute the thermodynamic limit of the joint distribution of points and cycles? And this could be done, and there are related results by Vogel and Dixon and Matthew Dixon and Kim Vogel, where they do it in a discrete setup, but the techniques are very similar to what you expect to do here, and also more recent results by Quitman and Taghi. Other thing you could do is consider, okay, go to the next level. So the next level is reintroduce interactions. There are some previous models where they consider weights on cycles. So these are not looking at the full-fledged interactions, but okay, you consider interactions by counting how many cycles you get. You introduce in the Hamiltonian some weights on how many RL. Here is the number of L cycles in sigma. So you start counting how many cycles you get of each type. And Betz and Woolsey in the same paper where they produce this Poisson-Dirichlet distribution consider some models like this, some limiting regimes like here. And there are also some results by Elbow and Pellet from 2019. Also, another thing you might want to do, this is an annealed model. Annealed means, in the setup, this means that we are sampling points and permutations at the same time. As Roberto mentioned, we could do something different. We could consider quenched models, where you first sample points according to the process you want, say Poisson process. You sample all the points and then you throw in the permutations. And these models are quite difficult. They've been studied in dimension 1 by Biskup and Rihammer in 2015, but the methods are very one-dimensional dependent. And there are some results in ZD when the set of points, this is when the set of points, they can treat general distributions of points, given that the points are separated enough. You don't want condensation of points because, of course, then you'd have very condensed cycles, but under reasonable assumptions, they can treat the general case. Now, for the higher dimension, there are some, this is incomplete, but there are some results in ZD. Things get more complicated, and usually these results have to do with not having the absence of macroscopic cycles. I mean, it's simpler to prove the absence by different methods of macroscopic cycles, but there are conjectures on when we see macroscopic cycles coming up. And of course, you'd want to also consider Poisson point processes on ZD. So you sample, say, on ZD, you put a Poisson number of points on each lattice point, and according to the Poisson process you're interested in, any density, and then you want to sample the permutations and see whether you see macroscopic cycles or not. So, but this is quite open. And finally, the full problem, which would be reintroducing V, which was, if you remember, this was coming from the interactions, pairwise interactions. So you'd get, in the Feynman-Kac representation, you'd get factors like this, exponential factors like this. These are the interactions of each cycle with itself. Of course, and then we'd have the Brownian bridges, but we'll get these extra weights with respect to the Brownian bridges distributions, and this would be describing the interactions of the cycles with themselves, within themselves, and the interactions between different cycles. And this is quite complicated because, I mean, this would be a very interesting thing to study. Yeah, we don't know if our methods apply here. As I said, all the independence is lost and it gets much more involved. So I'll stop here. And just a couple of...
Yeah, there are any questions, comments?
Do you have some understanding of the capital sector?
You see, we have the loops. I mean, for us, we only see the loops. We haven't considered, I mean, if you look at the finite box, what happens, in order to see the macroscopic cycles, what happens is in the finite, I mean, let's go back to the Betz and Woolsey results. What you see is that these very long cycles, which actually have size, they have size order n, right? I mean, they're size comparable to the total number of particles. Now, when you take the limit, when you take the thermodynamic limit, you don't see such long cycles. Cycles, if you take a finite volume, the intersection of the random interlacement with the box will be of order the size of the box to the square over D. So it would be like the length squared. This is what you expect from interlacements. So there's discrepancy here because the long cycles you were seeing in the canonical measure were of order n. The cycles you're seeing from the interlacements are order n to the 2 over d. What's happening here is that the long cycles essentially go to the border of the box, split up, and then you don't see this splitting up. So it's like they go to infinity and come back. And when they go to infinity, you split it and you get a new one. So I don't know, maybe this has to do with your question. I mean, I think I took a detour, but I think the continuity should be, yeah, you're seeing finite cycles, but long enough. The question would be, how long? But no, we haven't studied that. But yeah, I think that there should be a connection in there in seeing how you reach these macroscopic cycles, how you make a transition there.
More questions or comments? No?
Okay, so let us start. I would like to start this presentation by thank everybody for being here, the people watching the YouTube, and also giving special thanks for those that, in a way or another, is part of the history of this work. Professor Walter Pedra, Professor Rodrigo Bissacco, my co-authors, Professor Marcelo Larca, and also Professor Eric. And okay, so I will talk to you for you today about multidimensional contours, la Fleury-Spencer, and also a proposal for a boundary condition for quantum spin systems. So the overview of my talk today will be, I will start with some motivations, why I studied these problems during all these years, and then I will comment about what I found during my PhD. So, and I finish with some ideas for future projects. So first, I worked both in classical and quantum statistical mechanics, both equilibrium statistical mechanics. And for the classical statistical mechanics, I studied this particular model, what is called the long-range Ising model, that is described by a family of Hamiltonians. For each finite box, you can define those functions, and for a fixed boundary condition in the classical case, with each one of these Hamiltonians, I can define finite volume Gibbs measures, where these are all probability measures with the normalization given by the partition function. I also want to stress that in this case, I'm putting a modification on this model. This is really important. There will be a long-range Ising model with a decay alpha larger than 2, a polynomial decay alpha larger than 2, and also there will be a spatially dependent deterministic magnetic field. So why study this particular model? It's because this model has a very peculiar property. If you look to the pressure of this model defined by this, if you take a sequence of boxes, you can show that this exists, as Roberto already commented in his talk. And you can define a pressure or free energy, if you like to call it like that. And what happens is that when you consider the decaying field, for all kinds of the decay, the pressure is actually equal to the pressure of the Ising model with zero field. And as you know, for dimensions bigger than 1, and there is a point where the pressure is not analytic anymore. So if you believe that phase transitions are described by non-analytic points on the pressure, then you would conclude that there would be phase transition every time. But actually, if you look to the Gibbs measures, this will be not true. So what are the Gibbs measures? Well, you take the Gibbs measures as being the closed convex rule of the weak star limit points of the finite volume Gibbs measures, as I defined it for you before. And we always have that for discrete spin systems, you always have at least one weak star limit point here, basically because of the Banach-Alaoglu theorem. So a phase transition, in terms of the measures, will be characterized by the existence of more than one measure in this set. For ferromagnetic Ising models, you can use the FKG inequalities to show that these two special measures with different boundary conditions, the all plus and all minus always exist. And the strategy is usually to show that they are different using what is called a Pyros argument. This is a very famous argument in statistical mechanics, and it's very robust. So the usual Pyros argument, as you can see in Velenik's book, for instance, was actually extended for this kind of systems when alpha is larger than d plus 1 and dimensions and high dimensions is 66. So the problem, and also for more general systems, For instance, if you want to consider general discrete spin systems and also models that are not symmetric, then you have also an extension by Park in the context of Pirogov-Sinai theory, but now the decay should be really larger, considerably larger. So as you can see, as I am considering the model for all alpha bigger than D, my first question, also I must comment that these are results without fields. So the first question Rodrigo gave me to investigate was, can the Pyros argument be extended to the ferromagnetic long range Z model in the whole region of the parameters? So, but you can also go to a more general setting. You can consider a family of functions, of real valued functions indexed by the finite subsets of the lattice. And you can define this Hamiltonian here that already appeared, I guess, again in Roberto's talk. This is the empty boundary condition Hamiltonian. But what happens in classical statistical mechanics is that there is a way to generate many more Hamiltonians that are interpreted as being Hamiltonian interacting with the exterior through some boundary conditions. So what you do is that you add a term that will sum over all subsets that somehow see what's happening outside your finite set. Of course, there will be some convergence problems over here, so you cannot start with an arbitrary family of interactions and expect that this makes sense. But there is a quite general class where this theory works. So generalizing what we did before for the long range Z model, you can define these expressions right here. These are probability measures these are probability measures also, and are called also the finite volume Gibbs measures for this interaction. And you can also make the same definition. There always will be some point in this set, in this case, but you have also many more features for many more properties for this family of probability measures. The first one is that they are indeed probability measures. The second one is that for each f fixed, each f continuous function fixed, then you can see the probability measure as a function of the boundary condition, and you get that this is actually a continuous function. And more than that, a very special property is the property given by the following: if you have a continuous function and then you want to integrate first on a slightly smaller box, and then you want to integrate again by another probability measure outside, then it's the same as if you had started with the probability measure in the larger box. This has some nice interpretations. The first one is that these characterizes somehow the conditional expectations, but there is also a convex geometrical interpretation. That means that this measure is in the convex rule of the measures in the smaller box. So you can see in both ways. But what we get is a definition of another different definition, the DLR probability measures that are defined by satisfying this equation. Again, this has a nice probabilistic interpretation. You may see this as being what measures have these finite volume measures as its conditional expectations. And actually, a very nice theorem that is proved using a little bit of convex analysis. You can show that these sets, the set of the DLR measures and the set of the Gibbs measures, are actually equal, and you don't need it to be easy spin system. This holds in much more generality. So what is the second question? the idea was trying to extend this for quantum statistical mechanics. And what sparked our interest was some negative results from Werner and Thames in this paper, boundary conditions for quantum lattice systems, where they claim that the boundary conditions that I will talk a little bit more later, that are available for quantum space systems, do not generate all the equilibrium states that are characterized by the KMS condition. But there is this recent paper that Peter gave a talk about, I guess yesterday, where they were not studying the positive temperature states, but they were trying to understand the ground states, and they managed to classify all the ground states using some sort of boundary condition operators. So this raised a question if we could do something similar for positive temperature states. So the question is, can the DLR theory be extended to quantum spin systems? And okay, so our strategy for the classical problem is the following. When you are in the region of decay for the long-range easy model between d and d plus 1, in this region right here, then the system starts to interact more stronger than the boundary, let's say, and so the usual contours doesn't work for to separate the system in a nice way. So we need to use a multi-scale strategy employed by Fuller-Spencer in a series of papers during the 1980s. Where they were studying some classical statistical systems and also Random-Schroeder operators, and using their strategy, or better saying, generalization of their strategy, then we can define a multi-scale, some sort of multi-scaled contour that I will explain more, and then we can extend the Pyre's argument for this model. And for the quantum problem, the problem is basically classical DLR theory only exists because this holds in classical systems. And this can't hold for quantum problems, as Roberto already told us. You have a problem when you want to separate this. So you have to first try to find a substitute for something that can satisfy this property, and actually this substitute is the Poisson point process. And okay, so let's start. Our main result for the classical problem is the following. This is a result by myself, Sacco, Endo, and Handa, and we proved the following: for every dimension bigger than 1, we let the decay to be bigger than d, and the decay of the field should be larger than the minimum between alpha minus d and 1. So there will be phase transition in the sense that we can show that the plus measure and the minus measure are different. So a picture is usually easier to understand what is happening, and we get the following phase diagram for the system. So in this axis here you have alpha minus d, in this one you have the delta as being the intensity of the decay of the field, and what we can show is that there is phase transition in the gray area. What happens in this area right here is that we need to assume that the parameter h star that modulates the, let's say, the intensity of the field should be small. So we believe, since this result needs this condition to hold, we believe that all this white area over here, it should hold uniqueness. This is not so absurd because already in the the short range nearest neighbor is in model with the decaying field. This is a result by Rodrigo, Cassandro, Cioletti, and Presutti. They already showed that there is uniqueness when the field is in this region right here. So we believe that there should be uniqueness in this region here also. So what are the contours then? We follow first Pirogov-Sinai strategy. You first define for each configuration. You need to separate the points in terms of if they agree or not with the ground states of the systems. Since these are ferromagnetic easy models, this should be plus and minus. And then what we do is that we separate those points that do not agree with the ground state. So if they change sign, and we call the set of all these points that are called incorrect as the boundary set of the configuration. Again, a picture is much easier to see what is happening. Suppose that you have this local configuration here, and suppose that outside in all the white area you have the plus sign, and then in the next picture I will show what is the boundary of the configuration. So as you can see, this point right here, if you look to the first nearest neighbors, is all minus. So in the next picture, he is not here anymore. Okay, so you take away all. You only stay with the points that are incorrect, and then you get this picture right here. Of course, the boundary of a configuration can be, as I defined it before, can be crazy, can have many connected components. This one is nice because it has only one connected component, but you could have more components, and this could also be infinite. But we only stay with configurations that have a finite boundary. So the contribution that we gave to this problem is basically encapsulated in the definition of MAR partition. So an MAR partition is the following. You fix first three real numbers, and then we want to make a partition of the boundary that will be a finite. We will always assume for now on that the boundary is finite, and then it should satisfy the following. First, the first condition is that they form a partition of the boundary. So if you take the union of all the elements of the partition, you get the guy. And then there is another very important condition, is that each gamma prime that is different from another gamma is contained in only one connected component of the complement of the other guy. So again, a picture is easier to see what is happening. This is an example of something that doesn't satisfy condition A. So suppose that you have this set and you wanted to partition in something like that. In the green region you call gamma, and the pink region you call gamma prime. So what is the problem? The complement of the region gamma is the white part over here, and the connected parts are this one, the exterior one, this one, this one, and this one. So what is happening is that the pink gamma prime actually occupies three different connected components of the complement of the green region. So this is not allowed. This is what we are trying to avoid. So in order to get a partition that satisfies condition A, you should call each one of these sets a different name. So, and the other condition is actually a distance condition, and it goes like that. You have the R fixed. So we will say that we need that there should be another part, a subfamily, for each contour. That is, the number of this family is bounded by 2R minus 1, where the following happens. If you take the union, you get your contour, and more than that, they are separated by this condition. So this says more or less that they should be far apart. And again, this is quite technical, so a picture is better to understand what is happening. So suppose in this situation that we are trying to separate this set over here into two disconnected parts. suppose that each one of the gray regions you have a diameter of n, okay? And we are assuming m equals 1 and r equals 2. Therefore, we are only allowed to break our sets before calculating this quantity into at most 3 parts. So if each one has the same diameter, okay, so you can take this partition over here, and if you plug over here, you will see that since this one has only one connected guy over here, so you will have something like the distance should be larger than n to the power a, and since in this particular example we have the distance as being n to the a over 2, so this can't be allowed, so this should form a partition, the whole set should form the MRA partition. So we can also have another problem, because since the R puts a cap in how much you can, let's say, atomize your set. So in this case, if I have the same thing, everything being n, everything being like n in the diameter, I could make this work if I just choose the partition to have 4 elements. This would work in the picture. But since there is a cap in the number of sets that I can use in my partition, I cannot use 4 sets, so I can only use 3. And if I try to choose 3 sets, this is problematic. So this also doesn't satisfy condition B. So okay, for the contours will be a set that satisfies the MRA partition, and we always assume, as in the one-dimensional paper of Froelich-Spencer, we will always assume that we choose the finest partition that always exists. So we also will choose A as the parameter given by this expression right here. And actually this is very important, because it means that when your interaction is stronger, the interaction gets stronger when alpha is closer to D, then you need that the contours should be farther apart. So R will have this expression depending on A, and what I want to stress is that the one-dimensional Froelich-Spencer paper, the condition B that we have for distance is exactly our condition for A equals to 3/2 and R equals to 1. So there is always a finite, there is always a MRA partition, and I will describe the idea of how we can get the partition. So, okay. Let us suppose that we have this set, the boundary is just the gray area right here, and then what we do is we look to the points, and at each scale we will make graphs using the points. This first scale we use the points. We will make a graph, and then we extract connected components that are small. So in the first step is the step of the points. So you consider a graph where the vertices are the points, and they have an edge if their distance is less than this quantity. And if you do this, then you can take the connected components of the graphs, and then you count the number of vertices in this connected component. If it's less than 2r minus 1, in this case r equals to 3, so it should be less than 7. And then you extract and you go to the other scale. So in this case, this is the smaller one. I will take this away. So what we do in the next scale is that we cover the set with cubes of side 2 to the power r, and with center in ZD. Then we take the minimal cover of this set, and again we will produce graphs, but now the vertices are these cubes, and we put an edge every time the distance of the cubes are less than MdA2AR. Why this number over here? Because this is exactly the diameter of the cube, of this cube, in the L1 distance to the power A. So now again we count the connected components that have less than 7 cubes. This will be the one that we will take. And then we continue the procedure. So again, and now for the other scale, we take cubes of side 2 to the power 2r, and now the center is also scaled. So the center now is in 2r ZD, and we do the same. We take the minimal cover, and then we take away. You make the graph with the edges given by this distance, and take away the parts where you have less than 7 cubes. So okay, but what happens if I am in a scale and the graph is too large? There is no problem. You just continue, go to the next scale. Eventually, you get less than 7 cubes covering your component, and then you get the MRA partition being like this set. The different contours being denoted by different boundary colors. So okay, and the biggest problem with this is that first is the entropy of the contour. It means that when you try to count the number of contours that have a given support, the support of a contour is just the number of points in the gray area over here. Oh, sorry. We can get that this is actually exponentially bounded depending on the mass of the contour. And this is quite nice because usually this is also the bound for when you assume connected components, connected contours, and since this one is not connected, you can't a priori know what should happen. So, and the other important thing is the following: since now the contours are well separated, then you can extract the contribution of a contour. You should understand this as being you have a contour gamma, and you are trying to erase this contour, and you want to see what is the difference of the energy, what you get when you try to erase a contour, and what we can prove is that this is bigger than the size of the support of the contour. But there is another 2 terms that appear, and that depends strongly on the long-range nature of the model. And these f quantities here are defined as something like this, and this you can understand as something like surface terms. Okay, so and as you can see, I just put a nice lower bound, and you can see that there is a difference when alpha is between d and d plus 1. Okay, so again, what you get is this result. And basically because the field when you are summing over a box should behave as something like that, and when you compare the behavior of the field, I use the terrible color for this, yeah. It should be something like that. Okay, so a constant that depends on a lot of stuff, and then you have this behavior, and then you compare this exponent with the behavior of the long range, and then you can see that for the long range to win the contribution. Oh, it's before this one. Oh, this is a constant. This is a constant. So, and when you compare this exponent with the ones that you get from the long range, then you see the different behavior. Okay, so now for the quantum part, This I was talking with Roberto the other day. He actually beautifully explained what the physical meaning of groupoid should be in this context. I will not be so nice, but my idea was that the groupoid should be seen in quantum statistical mechanics in the same way that you see the configuration space in classical statistical mechanics. So this is the definition of a groupoid. I guess many of you already know. A groupoid is just a set equipped with an inverse operation that should be globally defined, and a product operation that's possibly only partially defined, and that should satisfy the following properties. The product with of an element with its inverse is always defined both ways. There is an associativity. If you have the product of G1, G2 defined, and G2, G3 defined, then this product and this product is also defined, and they are equal. And there is also this identity property. If you multiply by something like this, it should get you the same guy, and also for the other way around. So there are some distinguished sets. There is the unit space, the collection of all the inverses. Let's say all the units. And there is the range and source map that are defined by this expression. I will show a picture that I hope will clarify why this definition is correct. And also you have these preimages that they are important for technical reasons. So the way that you should understand the set of a groupoid is something like you have your G0, your configuration space, and then you have arrows that are coming from one point to the other. That physically means that there is a transition occurring between two different points of your configuration space. Okay, and the product should be understood as a composition of arrows, and where you start and where you go is exactly the source and the range map. So you can see that if you go this way and then this way, you get exactly the expression of the source that I showed you, and the other way around you get the expression of the range. Okay, so the groupoid for
when you compose, in which order you are composing?
Yeah, it's the opposite. Yeah, in this picture is the opposite direction, but in this picture I did on the other direction. Okay, yeah, this is confusing. Yeah. So in the thesis I did it on the other direction. Yeah. So now I should apologize to the groupoid community, because the groupoids in statistical mechanics that I'm worried about are quite simple. You just take a group as being the key roots of unit. The configuration space will be the product of these groups, and then you consider this the direct sum of this group acting by multiplication in its coordinate. Okay, I must say that I'm using here that lambda should be any set of ZD, so it could be infinite, and then you take on this set. This is just the algebraic part, but we are not interested only on the algebraic part. We need a topology, for instance. So you can consider on this set just the product topology. This one has the discrete one, and then you take the product of the discrete topology. And for this group, you can take the discrete topology also. I put a metric on the thesis, but you can see that metric is actually generating the discrete topology in this group. Okay, so and what is the product? Is the following, as Roberto asked. I'm using the composition the other way around. You start with the set, and you move, and you start in this configuration, and you move by the element G to the range G sigma, and then you go with H to the other part, and then you compose it by this rule. The inverse is something like that. Actually, these are just the transformation groupoids that Johannes told us on the first day. So and the nice thing is that the unit space is just the configuration space in disguise. You just put the unity of the group on the right side. So it's essentially the configuration space. So the range is where you are, the source is where you start, and the range is where you are flipping your configuration to. So for now on, I will just consider not now, but at some point of this talk, I will only consider the case Q equals to 2. In the case Q equals to 2, this is just Z2, and then this action is known by those who study statistical mechanics as the spin flip action. So you're just acting on configurations on classical Ising spins by flipping the sign of the configuration in a given subset. So okay, since now we also have a topology, as I told you before, we can define this this space over here that can have a star algebra structure given by the adjoint operation is given by this expression right here, and the product is a convolution product. You can see that if you assume that these functions are some sort, let's say, classical, meaning that they are zero outside the unit space, then this product recovers the usual the usual pointwise product of classical statistical mechanics. But in general, this will be non-commutative. Okay, so how to get a C-star algebra? You first need to represent it in a given Hilbert space. I will not discuss much about this, but I use the reduced groupoids C-star algebra construction because there is a nice Hilbert space where you can work on. And then the first proposition that is well known actually is that for any point, the C-star algebra of the groupoid, if you consider the sets of only one point, is just the matrices. For the general Q, is just MQ. Over here. For any finite subset, the C-star algebra can be shown to be isomorphic to the tensor product of these ones. And more than that, if you take lambda to be the whole lattice, then this C-star algebra can be shown to be isomorphic to the quasi-local algebra of observables. So important functions that already appeared, for instance, in Abel's talk, you can see that the Pauli matrices in the z direction is just this function that only sees the. Actually, there's something missing here because this is actually a classical function. So this is only sigma x if j equals to 1. I'm sorry, and also gx is just the element that flips only in x, and all the other parts of the lattice you have just the identity. So okay, and inspired by this, inspired by this paper by Kochimansky, that is actually a physics paper. When you go to the groupoid picture, you can actually find a family of Jordan-Wigner transformations that goes like this. For if you define the annihilation and creation operators by these expressions right here, then a Jordan-Wigner transformation will be defined once the functions, the family of functions that you chose, that can depend that can depend in all points beside x. If they satisfy this equation right here, then you get a valid Jordan-Wigner transformation. So just to show you that this is not an empty, that there are some functions that satisfy this condition. If you define some sort of kernel in ZD, a real valued kernel that in the x-axis equals to 0, if you define the functions by this expression right here, as you can see, this condition is exactly so it doesn't depend on the spin at site x. Then that equation is equivalent to this one. And then if you plug for d equals to 1, the delta function in using the usual order of the chain, then you'll recover the usual Jordan-Wingler transformation that you see in physics classes. But in the larger than 2, if you use, for instance, the lexicographic order, then you can see a Jordan-Wingler, multidimensional Jordan-Wingler transformation. So the main points of why to use groupoids is that this is actually something that Roberto told me when I was visiting NYU-Shanghai, that this is interesting. You can see the operators on a C-star algebra, actually a dense set of the operators in a C-star algebra as continuous functions in some space that is the configuration space. Let's say the quantum configuration space. Also, as Roberto also told, the states now can be described by family of positive functions, positive as operators, that have some condition with respect to the partial trace. That this is true for the quasi-local algebra is actually in Walter's Pedra and Bru's book. This is proved for the quasi-local algebra and also holds for the groupoid C-star algebra because they are isomorphic. And also you get a family of Jordan-Wingler transformations. So, okay, what about the runner representations? As I told you, before I tell you more, I want to know how much time I have. 15 minutes? 20, okay. Okay, it will be enough. So the most important part is that this is lost when you go to the quantum world. So you need a substitute for this property to have for instance the consistency condition of the DLR equation. You need a substitute for this, and what we actually try to do is to use the Poisson point process. So, and the idea to introduce random representations for quantum spin systems is not some unusual thing. Actually happened in many places, as Inés explained it to us in her talk. But I just chose to show some papers that I read a little bit during the development of this work, and one of them is a paper by Eisenman and Armendáriz, where they use Poisson point process specifically to quantum spin systems, and they also tried to tackle this question of how to describe the states as some measures, and then they defined this notion of quasi-state. But as of today, I didn't saw anyone trying to further investigate this property. So, but there is also other paper that is actually much more general, is a paper by Abel, Klein, and Landau that's here. Actually, Marcelo already talked about this paper. He mentioned his paper also, and it's a paper that relates some stochastic process to some KMS states, because and why I use some, because he needs some positivity condition to hold. So, and it's also apart from that, it's very general. So, and also this one by Jim Mazioff is actually a chapter in this book, Stochastic Geometry of Classical and Quantum Easy Models, that is very interesting because he puts all kinds of random representations, such as the FK representation and random cluster, random current representation, in the same footing as being some, let's say, some shadow of a Poisson point process acting behind everything. So, okay, so what is behind the idea of a random representation? The idea is actually quite standard. If you, as many of you, I guess, already know, you just use the Lee-Trotter formula and you write the identity. You have to write the identity operator as a sum of projections in a clever way. And for now, I will assume that our Hamiltonian systems are given by this expression. This is actually a very, very general. Every local function is a polynomial. Every local function is a polynomial on these variables. So for empty boundary conditions, this is actually all the kinds of Hamiltonians that you can get. So, and where FB are like classical polynomials defined by this expression. So, okay, what is a post-1-point process? A post-1-point process is a random counting measure that follows a Poisson distribution, and I used this notion as a random counting measure, but I wanted to think in more in a more physical way, that is understanding these counting measures as being paths, but I don't want you to try to calculate stochastic integrals in a space of paths. Just bear with me now. So, okay. Now, what happens is that also you cannot calculate the exponential of let's say, let us call this the Gibbs density for now on. So the Gibbs density, you cannot calculate it as a function on the groupoid. You cannot calculate its values by just knowing what happens on the Hamiltonian. So what you do is that with the help of the random representation, you can expand it as an integral over, let's say, again, this right now. So first, these, as I told you, should be understood as paths, but they are really counting measures. So what do I mean by that? This set is just the set of all the counting measures. I'm writing in this way, assuming already that the times over here are ordenados. How do I say this? Ordered in an increasing way. And then I put the following restriction: BK should be a subset of ZD. And since we are in the case Q equals to 2, the case Q equals to 2, you only have spin flips. So in order to define a non-trivial element in the group, you just need to define the set where it acts, where it flips. So you take the set BK and you construct the element of the group GK, and you ask that the next configuration will be exactly the last configuration flipped by GK in the subset BK. And now with this counting measure right here, and understand it as a path, then this notation makes more sense. This notation that I wrote right here, that is different, of course. So, okay, I'm sorry for that. And then this notation makes more sense when you think of this counting measure as a path. So this, you're just integrating a locally constant path. So in a picture is always easier. So if you take, for instance, a counting measure that only represents two jumps, then it should be related to a path by something like this. You start at sigma, then at the point T1 you jump to the next configuration, sigma lambda 1, and then you go into T2, and then in T2 you jump to the final configuration. Okay, and the other important part is this one, and this will be actually, let's say, this is the quantum part. This is the most important part of these random representations, because it deems it non-trivial. Actually, the transitions in the quantum system are encoded in this function right here. So you take the path, you can produce a path on the groupoid, and then you just calculate the product of each one of these terms over this path on the groupoid. So, and as you can see, you can have many different paths. When you start at sigma and you go to G sigma, as many of you may have already noticed, there is only one way, because the action in this case is free. But if you look to paths, this is not true anymore. There are many ways to start in a configuration and go to another configuration through the paths. So, for instance, you could have started by just flipping the blue region right here, and then flip it the other blue region here, or you could have just flipped this L-shaped region here, and then flip it again the missing part. So in that integral, you should consider all these cases. Okay, so what is the idea of a boundary condition that we arrived? You have this path that is evolving from one point to another. So what we thought was that maybe if we can fix the path outside the box, then we should be able to get something close to the DLR condition. So now I will assume that all the interactions have finite range. This means that in that expression that I wrote to you, this is a sum over here plus FB sigma B1. Then to be finite range, it means that if the diameter of the set A is larger than 0, then R, this is the range, then JA is 0, and something similar for here. If the diameter of B is larger than R, then FB should be the 0 polynomial. So it means that you are just putting a cap on the Hamiltonian. You don't see the box everywhere. So okay, and how do we fix the path outside the box? So first we need a definition, an equivalence relation. If you take two counting measures, I will say that they are gamma boundary condition equivalent if okay, I didn't put this here, but there is an important thing, because one thing is the set B, another thing is the set B prime. B prime is the following. I define it to be the union of B with the support. Sorry. Oh, okay, yeah, okay. I went too far, so it's better if I go the other way, yeah. So this in classical statistical mechanics, we call the support of a function the number of spins, the spin sites where your function actually depend on, but since I already used support with another meaning, I will have to change it. But so this is basically the largest, the smallest set, where FB depends in the sense that if I change the spin inside the set, then the value of F will change. Depends on lambda. Okay, and then B prime is B and a union with this set. And what is a gamma boundary? What is a gamma boundary equivalence? If you look to two counting measures, then this, let's say, larger sets, the number of these larger sets that they see what's happening in gamma, they should be equal. And more than that, the times where these sets appear in the counting measure should be the same. So what this means, that these two sets will be boundary equivalent if the jumps that occur outside the box are the same. Okay, so in order and we define this smaller set of all the counting measures in a quite large space a larger space where they are lambda, the complement of lambda boundary equivalent. So this means that all the jumps occurring outside lambda that see what's happening outside lambda are the same jumps. So we arrived at this definition of a path boundary density that should mimic what you see in the runner representation of the Gibbs density. But now you are integrating only on paths that agree with the outside, with fixed jumps, and you also need a modification of the functions that you are integrating. So these modifications are something like this. First, you need to add this term, let's say this classical term that sees what's happening outside the box lambda, and then you integrate in the same way as you did before, but not only the free boundary part. You integrate also the surface energy part, let's say, and this quantum part over here, you make the product, instead of doing the product of only terms that are strictly contained in lambda, you make the product of all the ones that can see what is happening outside lambda. And as you can see, I defined B prime here. Okay, so what is interesting about this definition is that you can ask what happens when you don't have any jumps. And actually what you get when you have any jumps is that you recover a definition that already appeared in a generalization to quantum spin systems, to quantum systems of the Piragoff-Sinai theory done by Data, Fernández, and Froelich, and also by Boris, Koteski, and Uchi. But these definitions of boundary conditions where you don't have jumps, you start in a configuration outside the box and you stay with this configuration until the end. They appeared also in a much more general setting in the Israel's book and also in Simon's book. Sorry, 5 minutes. Okay, so during this work I had to restrict to a special class of interactions. These are called the stochastic interactions. It's not stochastic, it's stochastic. The physicists gave this terrible name to this kind of interaction, and they are characterized by the following condition. Outside the diagonal, they only have negative, non-positive values. So why this is interesting? Because when you do the runner representation, then something that is called the sign problem is not present. This means that all the densities that you have are non-negative numbers. So these are some examples of stochastic interactions. You can see interactions given by expressions like this, such as of this form you have the transverse field Ising model, the XY Ising model, and also you have the toric pole Ising model is something of this form. So this is the definition of the finite volume path Gibbs functional. I will not have so much time to express this, but this is trying to mimic what's happening on the classical setting. What we managed to prove is the following: we have a consistency condition, a failure continuity property, and also a notion of properness that if a function lives outside what your interaction can see, then this can actually fix the function. In this side it should be f calculated at some point depending on the path in the boundary condition. So what is again a Gibbs functional is the weak star limit points of these guys, and then the quantum DLR states are states that should satisfy this condition. And what we can show is actually that they are both equal. The proof is basically the same in the classical case, because it's just a use of convex analysis. So what is the main result of this part right here is that the set of all the quantum let's say the quantum DLR states and the set of the KMS states, because what we are trying to read is the KMS states. We have the following: you have an intersection, and this intersection is exactly the no jumps boundary condition. Okay, and we couldn't show if we don't know if this one is inside this or this one is inside the other. So future projects is cluster expansions for the long range easy model. We were also trying to study the random field with João. It will be the next talk. Also important things that are different from the short range case is the decay of correlations in the long range systems, and also try to use these contours in more general systems. And for quantum statistical mechanics, I intended to investigate a little bit more the finite volume dynamics, because I chose to define boundary conditions only look to the density matrices. But now there is a question, because quantum mechanics usually asks for dynamics. So what is the dynamics of these states, of these linear functions, if there is any? Also, in a paper by, the big paper by Fernández, Sokol, and Van Etter, there is also a specification theory for ground states. Everything we did was for positive temperature. So a good question is, because there is already available the use of random representations to study ground state problems in random in spin systems. So it's a natural question if you can extend the specification theory to this case, and also find an example of a KMSA that does not come as a classical boundary condition. And by classical I mean no jump boundary condition, and further investigate this case, and also try to extend to the case Q equals infinity, because these are the class of the quantum rotor models that are physically important. So thank you all for listening to me.
Okay. Is this better? Okay, thanks for the talk, and I would like first to congratulate Lucas. I think I was impressed with the range and the fluency that I noticed in your thesis. And I don't work on quantum statistical mechanics. I don't know much about that, so I will leave that to the experts in the committee. But regarding the first part of your thesis and your talk, I was wondering, you didn't mention everything. Your results are for d greater than or equal to 2, and what is the state of the matter in d equal to 1? I mean, can you show some?
In d equals to 1, there is a lot of works done by. Actually, they will be here. Yeah, there is works by Immaculata Merola, Cassandro, and Presutti, and I'm forgetting someone. Pablo also. What they did is that there is the phase transition result by Froelich Spencer. Just let me put the glass of water over here. There is the phase transition result by Froelich Spencer in one dimension when the interaction goes as 1 over r squared. Okay, and this they used the contour arguments, and they closed an open question that was proposed by Katz and Thompson. And what happens in the one-dimensional case is that it's very different, because alpha, to have phase transition, alpha should be between 1 and 2. Okay, so this is the borderline case. The other case was solved by Fernández using the hierarchical model. And what happens that after a long time, Merola, Cassandro, Presutti, Pablo, they started to investigate if they could generalize the contour arguments for all this region over here. And what they can get is that they can get a Pyros argument for between 2 and alpha star that is bigger than 1. I don't exactly remember the expression, but they can get the extension all over here. And with this, they can do cluster expansions, they can study phase separation problems and all sorts of that kind of problem.
But if you introduce a magnetic field,
Okay, of course. If you introduce a magnetic field, there's actually the result of our group. It was in Bruno's thesis, also Eric Endo, Violeta Russell, Rodrigo Bissacco, and Arnaud Vanetti. 5 people, and they studied this problem. Oh, there is also another condition: the interaction with nearest neighbor spins should be higher, large. Okay, in the paper by Merola et al. So what happens that in this paper with the decaying field, Rodrigo and the other authors, they managed to erase this condition over here, but at some cost, because they can do the Pyros argument only when alpha star is larger than, only when alpha is between some alpha lambda that is larger than alpha star. And they get actually the same expression as we did for the phase transition, so the decay of the field should be larger than alpha minus 1. And we get, let's say, the generalization, alpha minus d. Yeah.
And your contours, are they very different from the d-dimensional extension of the ones introduced by Cassandro and Ferrari, Merola, Presutti, I think?
Oh, their contours depend on the
Your
fact that they
contours.
are my contours.
Yeah,
Okay.
would they be d-dimensional extension of those? I mean,
I don't believe so, because they use the fact that they are in that chain, because what they do is that they use the notion of triangles, and it's something that makes a lot of sense in a chain, but in the high dimensions we had some trouble to understand what a triangle should be. So what they do is that they separate, let's say, triangles, and their contours are like collections of triangles. Our contours should be understood as more like collections of connected components of
Yeah.
GD. So
more or less, okay, that would be the connection.
yeah,
Okay, thank you very much.
okay, thank you.
Okay, so I'm going to concentrate on the quantum part,
Okay,
which is really very interesting to me. So first, I would like to ask about the boundary conditions.
okay.
So you claim that your jump boundary conditions are more general than boundary conditions described by states, like in Simon.
Yeah, they are more general. Let's say they are more general than when you fix one kind of state, because what happens is that when you consider general states, in a quantum setting, if you plug, let's say, a classical interaction, what you get in the Israel boundary condition, just to make it clear, a classical interaction with Israel boundary condition, then you get a boundary condition that is actually an integration of the integral term. So in the integral of the other part. So what I wanted to say with more general is that if you take the limit of these states, you satisfy the DLR equations that we found. You can show that they also satisfy the consistency condition. They satisfy everything. So in this sense, they are more general. And but in an interpretation directly with jumps, I don't know if it is available connection between a boundary conditions with jumps and the state. Basically, because when you use the boundary condition as a state, you preserve the property that the density is still a positive density, and this is something that I believe that we lose with some boundary conditions here. You can restore it. You can restore it in some cases. For instance, if you consider the paths to be symmetric in time, let's say if the boundary condition is something like this, then you can recover positivity, but they are not. I don't know if they are all positive, and I believe they are not. So also this is in another sense that these linear functions should be more general.
But you claim that they are still visible.
I don't know. Yeah. I don't know.
Another thing that interested me is your notion of weak Gibbs, which looks very much like dynamical system boundedness.
Yeah.
So you prove that the weaks are contained in the weak Gibbs.
Yeah,
Can
we
you
actually
hope the opposite?
found a problem with our argument. So this is why I didn't talk about this today. But this is a very interesting problem because it just appeared on the literature. It's a paper by Alan Pilet, Tauber, and Yaksik. They generalize the notion of weak Gibbs. We think that it's actually because the equivalence in the weak Gibbs equilibrium and the LR is more natural to do. So we believe that this could be an application for the DLR theory that we are developing, but we couldn't fix the proof in time.
So my last round of questions is, so you have very original representation in terms of this process. Usually they have nice geometric representations, arrows here, going here and there.
Yeah.
You never mention something like that. And
Yeah.
I wonder whether it's just because you're lazy to draw, or it's deeper than that. And if this representation could give you some geometrical interpretation of phase transitions, what will happen in trajectories
In this context. Okay, there is actually a pretty there is a difference because what happens, for instance, in the paper by Nachtergali and Eisenman is that they treat the quantum and classical part in an equal footing, and then they can derive some representations that have a meaning of some sort, like flipping into points and stuff like that. But I chose to treat them in an asymmetrical way because, as you can see, the classical part is in the exponential. And when I do this, I can work with antiferromagnetic, for instance, antiferromagnetic interactions right here. I don't have problems with sign, since they are inside the exponential. So this is why I didn't have a more clear geometric interpretation. Basically, because I don't treat the classical quantum part in the same way as Eisenman and Nachtergali.
So I would be interested in knowing how useful is representation to prove additional things. So for instance, when you use your representation to prove continuity with respect to some extra parameters.
Extra parameters.
Zero, and whether your representation will show the continuity.
Actually, this is a good question because it is different from, for instance, as Bjornberg's. Do you know Jacob Bjornberg? Jacob Bjornberg extended the results on continuity of the magnetization for the quantum-easy model, for instance, and he uses the random representations by Bruno and Nachtergali. And this is exactly is a different representation. So I don't know what should happen. I don't know what should happen. Yeah, the student of agreement. Yeah.
My last comment is that you use Trotter. You have the alternative of using Newman, which gives you directly the continuum. Very much favorable to Newman. Trotter has this extra n. Then you have to prove results uniform in n,
Yeah.
which is a waste of time.
Yeah, exactly.
My advice.
Okay.
Okay, thank you very much. Very clear presentation. It's a nice novel representation that still you owe all of us the big question whether with your boundary conditions you can reach
All the
cases.
KMS.
But that's... Thank you
Thank
very
you.
much.
Lucas, first about the spin system, the long-range spin system. Can you hear me? Ok. Tá bom? Tá ok? Tá bom, obrigado. Okay, Lucas, about the spin system.
Okay.
You say that you use ideas of the Frolic Spencer paper on Austerlitz towers, right?
Oh, I used ideas in. What I tried to do at first was to define contours in a d-dimensional setting as like projection of the one-dimensional Frolic Spencer. This is where I started. Of like in Z2, what I tried to do first is that the contour should be the shadows of the contour should be the contours of the Frolic Spencer, and of course, this didn't work. So then I went to the Costa-Litaules paper and I started to look try to define something. But there you have a two-dimensional setting. So then I went to the Runner-Schrödinger operator paper where they do there is this section about like entropy bounds or something like that, and there they do the smooth scale in the d-dimensional setting. And
Yes,
this is
but
where
what they do, I mean, in what I think you are doing,
Yeah.
the contours appear. You take sigma, you have the contours.
yeah.
What Frolic Spencer do in the original paper is then to define what are singularities or resonances, depending what you are calling, and try to have a geometric description, probabilistic geometry, at least in the Runner-Schrödinger operator paper, probabilistic geometry. I mean, to describe the geometry of those resonances or singularities with some probabilistic estimates. You don't have the probabilistic, they didn't have it in Costa-Litaules either. They do something somewhat different. So they don't define contours. The contours just there. They work at the Dreyfus does the opposite. To define the boxes and then you fix the thing. But the way they so what replaces the probability thing? Because you are probably counting how do you make the decomposition, the gamma bars, right?
Yeah, yeah.
And then you probably have to have combinatorics to show what you get, and then to show that the decay beats it.
Yeah. Yes.
Yeah.
So what substitutes this is something that we call the total volume. The total volume is defined as something like that. You will look through your contour, and then you will sum over. In each scale, you need to use a certain minimal number of cubes to count it, to cover it. So you sum over all the scales, starting with 0. The scale 0 are just points, so you start with the whole volume of the contour. Then you go to the next level, you count the number of 2 to the power r you count the number of cubes of side length 2 over r that you need to cover it, and you go all the way until you reach the point that you are summing only one cube, because at some point the diameter of this cube will get large, so you would still be adding 1, so you just stop at this point. So the combinatorics, and this is where we were highly inspired by the Runner-Schrödinger operator paper, because he controls this quantity, not the volume. He doesn't count the number of contours that have the volume. He counts the number of contours that have a total volume. This means the volume in all scales bounded. And then the other problem is to show that for the contours given by a MRA partition, they actually have a bounded total volume. This is another problem that also comes from Frolic Spencer. Yeah.
And using it to construct what used to call inclusion facilities within class representation.
Yeah.
The Kenyan states can. I mean, that's not what you're trying to do. You're just trying to construct examples of applications or positivity. So basically, we're just trying to construct a classical representation of a quantum system. But you start from quantum system, we go more general, right? And you construct is not a classical representation. What's in terms of this representation?
Okay.
What you started with.
I'm not quite sure I understood the question.
No, my question then is the following. What we're trying to do, and I think Eisenman
Yeah.
that they do is have a quantum system, you construct some sort of classical system with
Yeah.
everything commutes, and you can do the usual things that you know. You starting with groupoids and something defined there, and then you construct some
Yeah.
representation on which you can define things. What are the properties of these representations that are really different from what you started?
Okay, so the first property is first if you insist in doing classical representations, then what you usually do, for instance, you can like restrict your state in an abelian sister algebra and do your calculations there. And what actually happens is that if you stay with these restrictions, they only stood this restriction, then they may lose Gibbsianity, and this Gibbsianity, they maybe not Gibbsian anymore. They can be not Gibbs. There are some that you can actually find a classical potential. Actually, it uses cluster expansions to do this. Such that the restriction will be Gibbs for this potential, but it's not true for the whole region of the parameters. And this is actually a recent paper on Journal of Mathematical Physics by Christian Maia. It's called locality and something like that, because what happens is that you may lose Gibbsianity. So in order to get a full DLR theory and Gibbs, you should not stay only with classical restrictions. You should see the full picture of quantum statistical mechanics of the groupoid. This is what I think. It's my opinion. Yeah, it's quite complicated. Yeah.
Thank you. So first I want to like to congratulate you with your thesis. It was very interesting to read. I didn't know much about classical mechanics. I feel I know a bit more now, so that's very welcome. So I will stick to the quantum part with my questions.
Okay.
So first I also want to talk a little bit about this groupoid picture.
Okay.
So how much do your proofs actually depend on the specific groupoid that you're using? So you use this groupoid that you can map to a quantum spin system, right? So one of the things that you mentioned at the very end, natural question, is to generalize it to infinite things, this quantum photo model. Or, but I guess you can use some more abstract groupoid. Do your methods still work then, or what do you actually use of the underlying groupoid?
I suppose that I use. I don't suppose I use very much the structure of a transformation groupoid. I don't know if I can generalize it to, for instance, the groupoid, the sister algebras and groupoid community usually they understand a very specific kind of groupoid called the tau groupoid. Actually, there are some works of like Thiago who already studied DLR equations in this context. I don't know if my constructions would pass to this kind of generalization. To this kind of generalization, but I think it is it's the next step if you want to stay in stay in this part, let's say discrete. For the case where you go to Q equals infinity, I don't know even what the groupoid should be. But I feel that the state space should be S1, but for the group I don't know what should be, and this is something I want to investigate more. A characterization, the DLR. Yeah, and there is a relation between KMS and DLR in this case, but the dynamics have a restriction on the center, so they are not like take any interaction and do something. There is a priori restrictions on the kind of potentials that you can deal with. So I don't know if I don't know what should happen in the general, by, let's say, étale groupoid case.
So another question that I had that you mentioned at the very end of your last chapter is, so you're thinking about if you can extend this to ground states. Could you maybe say a bit more about this? So what are the kinds of maybe the theorems that you would like to prove, or that you maybe the results that you would expect?
Oh, this is actually based on there is this paper on renormal. You can search Google for this paper by Vanenter, Fernández, and Soko. And they were studying renormalization group pathologies, and I guess in Appendix C, they discuss a specification theory for ground states. The specification theory for ground states should be a little bit different from what you see in the for the positive temperature case. I don't know much about the details, but I think it's worth investigating. And in this case, it should pose another kind of problems, because random representations for positive temperature can be seen as some sort of Poisson point process on an interval 0, 1. So to go to the ground state, the first technical problem that you would encounter is that it's more natural to study a Poisson point process on the real line. This is the first technical condition, and that you will get when you go to this place. And I don't know, maybe it's an interesting project to see, because you already have a declassification of all the ground states of the toric code in this case, but I don't know if you can show that this may come as some, let's say, quantum ground state specification a la Roberto of the.
Yeah, that's but you see what you do to define the specification for ground state. You take the final beta specification and take the limit. Beta was of the specification. Then you ask for measures consistent with that new specification. So the ground states are really measures. They are not individual. If you go to the quantum, then what you need to do, you take the dynamic, the alpha, or the KMS states as a function of beta. Take the limit when beta goes to infinity, and hopefully you have an alpha infinity, and then you have the KMS states for this. That's what you should know. I don't think that anybody knows.
Yeah, and this procedure should work in the runner representation, but as I said, when you take the limit, you should get a Poisson point process on the line. So I don't know. Since I didn't study this.
When you do this representation, basically you add one more dimension. which is the beta dimension goes from 0 to beta. So when you go to 0 temperature, beta goes to infinity, you can consider
All the lines. Yeah.
and a new phenomenon, backing fluctuation.
Yeah.
Also,
Yeah. And I guess this marks a really good difference, because one is a system that have a fake dimension because it is an interval, and the other you have a whole real dimension because it's the real line. So I guess it's feasible, but should be a lot of surprises maybe awaiting if you follow this path.
Yeah, that sounds like a very interesting project.
Yeah.
So maybe one final question. Right. So you mentioned in the beginning of your talk that essentially one of the reasons why it's difficult to go from the classical TLR to the quantum one is that it's this thing with the exponentials, right? EX. Yeah. I think you erased it already. But
Yeah,
EX is not equal to EX times EY. So I was wondering, so what are the X and the Y direction? Are these in direction terms, or is the problem easier if you have sort of interactions or dynamics that are sort of almost classical, so that they, all terms commute or something like this, like in the Torah code?
Actually, this is a good question. I don't know, because if for instance for the toric code, the two parts commute, right?
Yeah.
So you have that property over there. So I didn't try to investigate this case because during the project I was thinking a bit more general terms where this doesn't hold always. But maybe if you specialize to the toric code where this equation is true, maybe something different can be said.
Yeah, there are actually quite many of these topological models that are commuting projective Hamiltonians, essentially. So there's quite an interesting class of models that's
Yeah, I will take a look on these models. We are actually searching for models where we can say something, and but in the positive temperature case. But I will of course take a look on these models.
Yes, that's all my question. Thanks very much.
Okay, thank you.
Just a short question. So, if I understand well, you consider Kelly state in general. You don't assume translation invariance, right?
Yeah.
So, but if you assume translation invariance, you know you have this nice description by a variational problem of KMS states result of Robinson and Araki. It extends to this well-known result for classical systems. Did you try to do this, for instance, if you assume that your quantity large state is translation invariant or periodic in space, that it minimizes free energy density or not? Did you try something like that?
No, I didn't try. Actually, when we found this Wiki-Gibbs definition, this goes in that direction, because the Wiki-Gibbs definition actually lives in the invariant, the translation invariant case. But I didn't try to see what happens for the variational principles. Yeah.
So now this was the public part of the defense. Now we start the secret part. So I have to ask you to leave the room for a moment, then I will tell you.
Okay, thank you.
So as you have seen, it was not very difficult to make a decision. So I think we met the first time 6 years ago, 7 years ago, something like this. So he attended to a few courses of mine, and we discussed a lot. I know, so I have a very good impression of Lucas. No? I think he's really very talented, and it's really a pleasure to be the person that will announce that you get your PhD title. So congratulations, also in name of
Oi? Não, não precisa não. Agora é só parabéns mesmo.
speak about long-range probability.
Thank you. So I'd like to start first thanking you all for coming for the conference. I don't know if you saw here, but we took a picture of Rodrigo's group. And it's very important for me that I'm finishing my PhD to the graduate students that are here, undergraduate students that are here, to see that we are working with stuff that people are interested in, and we can actually work with stuff that other people are doing so. So really thank you. I can speak for everybody in the group. Thank you very much. So today I'm going to present a long-range random field easy model. This is a joint work with Lucas and Rodrigo. A brief overview of what we're doing. First, I'm just going to define the random field easy model. Then I'm going to define the long-range version. A couple of results on phase transition that we are interested in. Then I'm going to present this new approach for proving phase transition in models that you have some sort of contour system. And this model is a probabilistic one, so at the end we're going to have to control some probability estimates. That's the last part. So let's start defining the random field easy model. Again, Lucas defined almost of this in this place. So in this first part, I'm going to go very fast, right? So take states minus 1 and plus 1, you take the configuration space, and we look at general Hamiltonians. You have two body interactions. A one body interaction that is a field, can be any real number. And you have the interaction with outside of the box. We are going to restrict ourselves to positive interaction, so always ferromagnetic, symmetric, in the sense the interaction between x and j and x and y and x are the same. And we're going to ask that this interaction is bounded. The sum, if you fix a vertex and sum the interaction, this is bounded. The two main models we are interested in, you can think only of these two, is the nearest neighbor easy model. So we have interaction only if the spins are neighbors in the lattice. And we're also going to consider the long-range easy model. That's the same one defining. You have this polynomially decaying interaction. So everybody in the lattice interacts itself with this decay. And this alpha is just a parameter bigger than d. Again, this is the same definition, so we just take the Gibbs measures, the partition function, we take the closed convex hull of the weak limits, and we get the Gibbs measures. So, and again, the plus and the minus ones are the really important ones for now. And a result that I'm sure most of you must know is that, first, to show that phase transition is enough to show that the magnetization is with the plus boundary condition is positive. This is actually, in essence, what we're saying is that the boundary condition influences the spin to be positive, right? And we know that in one direction, in one dimension, there is no phase transition, no matter the temperature, by result by Ising, and Pyrus, which is famous contour arguments, could show that, but in dimension 2, or low enough, this external field. But the external field, we're going to consider random variables, Gaussian random variables. And this epsilon here, it works as the variance. So we multiply by x, we get the variance. So we have a field that is random. And in essence, what we are doing is that we are adding some competition for the boundary condition. So the boundary condition, in essence, tries to make all spins become plus, or tries to ordinate the spins, and this term tries to mess it up, tries to make the spins do not align. That's basically it. And we need to take some more care defining Gibbs measures, because now the Hamiltonian and the Gibbs measure are actually random variables. So you may ask how to define the Gibbs measure and so on, but we actually don't need to treat this, because you can actually show that the plus and the minus boundary conditions, these states, they exist, these limits exist almost surely. Just to say, when I say, P is the probability of is always the probability with respect to the external field. And as these two measures always exist, so we can define phase transition as usual. So if these two measures are different, P almost surely, then there is phase transition. And if they are equal, again, P almost surely there is uniqueness. And again, as in the usual easy model, we can show that phase transition occurs when the expected value of the spin is positive, but we have to take in account the expectation regarding the field. So when this happens, there is phase transition. And again, the natural question is if the field actually beats the boundary influence. This was actually there was a debate actually in the 80s when this would happen or not. So there was basically two diverging arguments in the physics community, two predictions of what should happen in this model. The first prediction in 75 by Maia said that for dimensions bigger than 3, there should be phase transition, and for low dimensions 1 and 2, there should be uniqueness. And the heuristic argument for his argument was that if you take a subset lambda, then the influence of the field on this lambda should be the sum of the external field. And if you sum the external field, these things behave like the square root of the number of sites in this fixed subset. But if you look at the influence of the boundary, if you take the side of the boundary to measure the influence, by the isoperimetric inequality, you have that this boundary is bigger than the size of lambda to this power, 1 minus 1 over d. So you can see that for dimension 3, this boundary influence is always, no matter the set, is almost bigger than the influence of the external field. So there should be phase transition. But on the d equals 2 case, for example, these things match. In essence, what we're saying is that if you take this lambda as a box, then the influence of the boundary is the same as the external field, so this should disrupt the phase transition. But as I said, there was a different argument by Parisi and Sorlas that they argued using some physical intuition that the random field easy model should behave like the normal easy model, but in dimension d minus 2. So if you follow this intuition, what you're saying is that there's only phase transition for dimensions bigger than 4. And for dimension 3, for example, you should have uniqueness. And this is actually a very nice example of when mathematical physics actually help the physics to solve a problem. Because after some time later, in 88, Brickman and Cupiani, in this seminal work, they could prove that Ingram prediction was actually right. And the model actually presents phase transition in dimension bigger than 3. You just need to ask that the variance of the external field is small, which is a very natural assumption. And the uniqueness proof came from Eisenman and Verne, that they showed that there is uniqueness in dimension 1 and 2, as predicted. So more recently, I should say, there was this new proof by Jing and Zhuang that they show the same result as Brickman Cupiani, but they avoid using renormalization group, because the proof in Brickman Cupiani is also famous for being very hard to understand. It's a 30-page proof that uses very difficult arguments, renormalization group, for instance. So they showed another proof, 3-page proof, very simple, and hopefully I'm gonna introduce this to you today. And after that, in a recent work, also with his students Liu and Xia, they could show that the phase transition, the temperature actually, sometimes you recuperate the usual easing temperature. So if this BC is the critical temperature for the short range easing model with no field, then if you take a smaller temperature, you can get, you can find a variance small enough that the random field also presents phase transition. Now we are interested in the long-range model. Can we replicate this sort of result for the long-range model? And again, I'm going to go very fast for the definitions because I think you already know it, but we consider the long-range model and we do the same. We add the external field in the same hypothesis, a Gaussian random field with a variance. And here I put some history works on the random field, on the long-range model. Well, as Lucas covered in his presentation, maybe I should just skip that part. Okay. This is the result he mentioned, the two-dimensional result by Fernández Spencer. The one-dimensional result, yes. I'm just gonna three dimensions, three or more. No, short range. I wrote long range. No, short range. Yes, long range order. Yes.
It is long range, but right.
Yeah, but the right long range, yes. Just one important result for us is that paper by Gibbs, Grossman, and João, that they showed that the usual pairs argument should works when you have alpha bigger than d plus 1. And okay, but the important question is, what do we know for the when we put a random field? What happens when we put a random field? And speaking about uniqueness, in the same paper that Eisenman were treated the short range version, they said that the long range version presents uniqueness again in 1 and 2 dimensions if this parameter alpha is bigger than 3g over 2. So in this region there is uniqueness. And the only result, as far as I know, for long range phase transition is by Cassandro and Picot, that they use their one-dimensional contours to prove phase transition in this region of. And again, they asked that the first neighbors interaction should be big. Here, I think I'm going to add a comment that Lucas said that in a paper of Bissacco, they can remove this condition, but they enlarge this alpha region here. But for the long range, you can actually do that and you change the contours, but you still need this assumption to control the effect of the random field. So you cannot, yes.
Okay, but I think it's just because we didn't try.
Yes,
yeah. Okay, you don't believe, but
I don't know.
if there's a debate, okay.
Yeah, there's a debate. So what we can actually show is that for the dimension bigger than d plus 1, as expected, there is phase transition for the long range model. And as I said, we're gonna basically use Gibbs proof together with Schneeber and Grossman-Well argument. So what's this new approach for phase transition? The idea is quite simple, so I could not think of a physical interpretation for it. But the idea is that we are going to do the pious argument, the usual pious argument, but now we're going to consider this joint space. We are not only evaluate Gibbs measure, we also need to take into account the random field. So you take this joint space. This is the density function of the joint space, so it's just a Gaussian density function and the Gibbs measure. And if you take this tau AI transformation, this is just transformation. You take the here I took from R to the D to R to D because I want to apply this not only on the configuration, but I want to apply it on the external field. But in essence, you take the value you put here and you flip everything if you are inside the region A, and you don't do anything if you are outside of it. This is in essence the transformation into erase contours. And what they do is that when they erase a contour in the user, usually what we do in the user Pyros argument, we just flip the configuration and see what happens. But when you do this for the random field Disney model, you get a term depending on you get a term that depends on the external field, but also depends on the configuration inside the contour. And it turns out that estimating probabilities for this thing is very hard. So the idea was, when we perform the Pyros argument on this joint space, you don't just flip the external field. You don't only flip the configuration. So when you're gonna erase a contour, you flip the configuration and you perform the same spin flips on the external field. So every spin that was minus and you put into plus, you actually flip the external field in the same sense. And why would you do this? Because when you do this, you get that here you get the energy cost of erasing this, of flipping this region, but with no external field. And these are things we can easily control using any sort of contour argument. And the dependence of the external field now becomes this quotient of partition functions. And these things here, first of all, they do not depend on the configuration. So these do not look at the configuration inside the contour. This is something that only depends on the region and, of course, on the interaction you look. But there is actually an even more important property of this quotient here, is that if we define this delta of A as just the logarithm of the partition function, which is 1 over beta. So basically, because when you come back here, then you have this interaction plus that delta function. So this becomes, we can actually show that this delta function satisfies these two probability estimates. So their tail, here we have to condition on the spins on the external field outside this region, but in essence we are saying that the tail of this delta function works like this. So to be bigger than lambda is exponential of lambda squared divided by the size of A. And when you look at the tail behavior of the differences, you get the same thing, but now you are dividing by the symmetric difference. And at first glance, it might be hard to see why this is useful. But what this is actually saying is that this delta function, it works, behaves in some sort as the sum of the external field, right? Because the sum of the external field has this exactly same tail. And if you just change here the delta by the sum, you get again the sum on the symmetric difference that has exactly this tail. So in essence, we are saying that this delta function has a tail behavior like a sum, and it actually works like a sum when you look at differences. Yes. Yes. So yeah, actually, this is a lemma. This lemma we can prove only if you assume that the external field is Gaussian. So usually we would like to extend arguments for when the external field is sub-Gaussian. So just the tail behaving like a Gaussian should be enough. But in this lemma, you have to actually use that is Gaussian because in essence we are calculating probabilities of a function of a Gaussian, and this is well behaved. So we cannot. It's much harder to estimate probabilities of a function of a sub-Gaussian because you don't actually know the full behavior of it. Yes. And okay, so contours argument. So let me just introduce it. The usual Pyros argument. So it's regions of the dual lattice. So I think maybe easier than to define is just to show a picture. So if you take this configuration, for example, You just, yes. No, you do the contours only looking at the configuration. Yes, yes. Sorry? No, they do exactly like this. Because when you have this decomposition here, you basically say that the external field plays no role here. So you can actually just use usual Paulo's argument to control this quantity. Yes, what they do both is flip this. Yes. You see, I mean, I could not understand if there is any physical intuition to this, but the mathematical consequences is actually very good. So we take the usual Paulo's argument. So for example, we have this configuration, and every time there is a different neighbor spins, we just put a line. Here is in 2 dimensional, so more dimensions are going to be the face of a cube. So we do this for every configuration, and the contours are just going to be these new curves. Yes, that's simply that. And another important definition is just the interior of the contour, but every region splits the lattice in an infinite component and a finite one, so you just take the interior. And we look at the contours that have 0 in the interior and have size n. These gamma 0 n are these contours. And what Ginibri, Grossman, and Huel could show is that for these contours, the difference in the Hamiltonian is bounded by size of the contour times a constant in the here. And one thing that is important to say that this works for more general, maybe it's important, more general interactions. So if you take any translation invariant interaction, then you have to satisfy this sum. Basically, what you're saying is that the nearest neighbor interaction in this direction, this EI, is just the basis vector in the direction I. So if you take these weighted sums on the interaction, you weight by this is the ith coordinate of x, of vector z. So when your interaction wins against this sum, you actually can use the short range contours and you still have this bound. Maybe an important comment is that this is a bound, obviously, but I have a very strong impression that this is actually quite accurate, in the sense that if you want to work if you want to work, for example, in the region alpha between d and d+1, I don't think you can do something better than this using short range contours. But anyways, if you have satisfied it for every direction, you can reprove this. Now, what is left to prove is that when you look at the supremum of all the contours, that error function that is competing with the energy cost is actually always smaller than the size of the contour. And why? Because suppose we can in some sort control this probability, then you look at that joint space and you look again the probability of seeing a -1 in 0 with the plus boundary condition, and you split it in the bad and the good and the bad event. In this bad event, you just bound it by the probability of the bad event. And on the good event, you know that the error is always smaller than 1/4 of the size of the contour. So you can actually just use the standard Paulo's argument, and everything should work to bound this bound this quantity by the usual term. And So the job now, so they don't take this delta, they take sums of random variable, and they try to assume general hypothesis on this distribution. And here they always look at connected components, so the same as us, but usually they take the sum and they divide by the volume. So they divide by how many sides you're summing. But here we want to do something different. We want to normalize it by the boundary size. And so we need some work on the probability estimates. And in this paper of Fisher, Froelich, and Spencer, they could actually show that this probability is bounded by exponential of a constant times the variance squared. To be fair, they didn't actually prove this. They proved it for another error function, but this error function, they had to assume that it behaved like the sum. They couldn't prove that it had that proper behavior. But if you change their function by our function that have the desired properties, you can actually show this. And after, I think recently, Ding pointed out in a paper, he made a comment in one of his papers saying that their proof is actually a non-trivial application of this Dudley entropy bound. The proof in their paper is self-contained, but there is a lot of, you can avoid a lot of calculations if you just use this entropy bound. And that's what we're actually trying to show. So what is actually this bound? So you consider a metric space, any metric space, and you take a stochastic process, as you can imagine, or delta functions. They have this property by that lemma if you consider this distance. So we are taking the square root of the symmetrical difference of two sides of the D, two subsets of the D. Well, so if you take this NTD as this is the minimal radius epsilon positive. This is a different epsilon, but it's not the same. So you take any positive radius and you count the number of balls you need to cover the space, and it's going to be this big N. And this Dudley entropy bound says that the expected value of the supremum is actually bounded by the integration, and you take the square root of the logarithm of this big N. I mean, the first time I saw this result, I was very impressed actually, because here you have any family of a stochastic process, and you are bounding this by something that is purely topological. There is no probability, there is nothing, this is pure topology. So it's quite impressive. Maybe another comment I'm gonna do is that we actually, I think as you can imagine, we're not gonna look at every radius here. We're gonna take some specific radius, but you can actually bound this integrate. So you go from 0 to infinity, and you have log the square root of n TD epsilon. Right, this quantity is decreasing, so as you increase the radius you need less balls. So we're gonna just bound this by some sort of step, let's say I going from 1 to infinity, and here we bound by steps. So we're gonna look at the difference in the step 1 and the previous step, I minus 1, and here you're gonna look at the log on the step. So TD, here you need to look at the previous step. Okay, so it's just a basic integral bound, just to discretize this thing. And the bound to, now we have to somehow apply this thing to our problem. Yeah, that's a very good question. I would say yeah, I'm not gonna give you any certainty, but I would say there is not much regularity need. For our case, of course, this is all finite, so there is no sense. But I would say it's a good question. I won't. Okay. So yeah, what's the strategy? So the strategy used this coarse graining idea. And the idea is that we're going to take every contour and we're going to approximate it by a simpler region that these steps are going to be some sort of scale. And for each scale, we're going to approximate all contours by some sort of simpler region. And what we're going to actually show is that if these two different contours are associated to the same simpler region, then the distance, they are in the same ball for some radius. This radius is going to be our steps. And yeah, that's basically the idea. So, okay, how do we do this? We take disjoint cubes. So this CMX is the cube on ZD with size 2m and center in 2mx. Again, pictures are better. So for example, this is the C3 cube. The big cube just says C30 cube. And the smaller cubes are C2 cubes for some center. So they are actually disjoint. And we're gonna say that one cube is admissible if, when you look at the interior, more than half of the cube is inside the interior. So we are basically taking contours and looking for fat cubes. And this BL, that's gonna be the region. It's just the region covered by these cubes. Sometimes we're gonna put the actual collection of cubes here. Again, let's draw some pictures, right? So you start. This is our contour. Okay, let's say this is our contour, and this small scale here, this is small gray cubes are the scale. So the size of this is 2L, let's say. So we just select every cube that has more of the half of the cube that is interior. So these cubes here on the boundary, they are not so much filled, so they are not admissible. So this is the collection of admissible cubes. Yes, this C is wrong here. This is not the C. This is the same C here, the frac C. Okay, sorry about that. And this is the first scale. So again, you increase the scale, so you increase the size of the lattice. You look at the cubes that are sort of full, and you take this is going to be your admissible cubes. And again, you repeat this, and you get more cubes. One important thing that happens is that this collection is now disconnected. You see, because sometimes your contour is going to have some thin regions. We call these corridors. These sort of corridors, they are thin, and then they do not connect the admissible cubes. And what we can actually show is that if you take two contours with side n that are in 0, and they have the same admissible region, if they have the same admissible region, then their distance in the D2 norm is bounded by this. So you have the size of contour, the square root of the size of the contour, and you have this 2L lambda, 2L over 2. This is actually the scale, right? So it's just a scale and a square root. And you get this epsilon here because of the distance. Yes. So we get a bound first. We get a good bound on the contours. And because of this, what is immediate is that, okay, so now if you want to estimate the number of balls with this radius here, so we can just bound it by all the admissible regions that appear when you vary overall the contours, right? Because every contour is taken in an admissible region, and two contours are in the same ball. So you can stop looking at to count the balls. You just need to count these admissible regions. And after that, you show that the number of such admissible regions is exponential n to L d minus 1 this is another constant before. Let me give you some intuition on this proof. First of all, this n divided by 2L d minus 1 comes from the number of cubes in the sort of the boundary. So, for example, if you take this collection here, you can say which cubes are in the boundary, right? So these cubes, all these cubes are in the boundary, and these cubes here in the interior are not. And you can actually show that in the boundary, if you take, for example, this cube in the boundary and this one here, yeah, if you look at how many points of the contours are here, you can show that there are 2L d minus 1 points here. So the number of terms in the contour here is something that resembles the size of, it's a constant times the size of the cube. I mean, the details of the proof of this were not very clear in Fischer-Fröhlich paper. They just said, yeah, this is true, consider the projections, and that's it. But turns out that intuitively, if I say this to you, I think nobody would disagree that this is false, right? Nobody would expect this is false, because you have a cube that is half empty and a cube that is more than half full. You should have a lot of points there. But I mean, there is no intuition for dimensions. I mean, what are you saying? So it was quite hard to generalize this to show that for n dimensions this actually happens. But once you do that, you get that the number of cubes in the boundary is something like n to the d minus 1, right? You have a constant. So you have these cubes in the boundary. You can show obviously that counting choosing the cubes in the boundary and choosing the volume is almost the same. Just have to pick an appropriate constant. And now what is left to do? Suppose we know that all cubes are connected, then that's done. This is just the number of regions is just exponential of this, right? But they are not connected. They can be very far away actually. So you have to use something to weakly connect these cubes. And what we have to do here, the only connection between these cubes is that they are enclosed by the contour, right? So no matter how far they are enclosed by a curve here or a surface of size n. And this is how you do to go around the disconnectivity. And the price you pay for this is adding an L here. And this is where the bound comes from. Yes, I have time, right? So, and the last part is just, well, let me go back there. So you have this, you have this, you have this. So this is the step. So you just change the step here to 2Ln, and you change this log of n square root by square root of this. And at the end, you're gonna get something like epsilon constant and to Ln, we have n, and you're gonna sum over L to the 2LD minus 2, right? And you can take the sum here going to infinity. These sums are all finite because eventually you're gonna only need one cube, but it's just and again, you see, this is why from here it emerges the D bigger than 3 restriction. So this is where it comes from. And so let me just comment about some future works we're working on. So now we have phase transition for dimensions bigger than 3. One of the natural questions will be to, again, see if we can extend this critical temperature to the temperature of the usual Ising model, on the long-range Ising model. Yeah, this is a very natural question for which I honestly have no clue, because the idea of the proof uses percolation, so we have to deal here with long-range percolations, and I don't know what could come out of it. Other question we are actually working on now, we're trying for actually quite a long time. We need now to enter the critical region of alpha between v and d plus 1. And turns out this is extremely hard, because let me just, for example, you have to use long-range contours to start with. You have to use long-range contours. So connectivity, you don't have it anymore. And I mean, all proofs that I know of, even for these, or when you're reaching 2 dimensions, they use connectivity very strongly, and you don't have these anymore. And maybe, yeah, I think, yeah. Maybe the set of contours now, maybe it's not only enough. You have to construct maybe a mid-scale contour. That your only concern now is not only bounding the energy cost of erasing. You have one other concern now, that you have to control how tight, in some sense, these contours are, because what happens that maybe your contour can be very sparse. For example, you define some logical contours that can be very sparse, that their diameter can be very large. These, I mean, if you try to count these, if you try to do the same with these admissible regions, you get a lot of entropy. It's very hard to recuperate something like this. But nevertheless, we think we can. We hopefully can do it. I mean, the last natural question is, of course, if we can extend in some way, in one dimension, we can cover the entire region, right? Because, well, intuitively, the region close to the critical value should be harder. So there is supposed to be a way that we can actually reach the whole region. And, well, I think that here are some references that I mentioned, and thank you.
Comentar só, volta no último slide lá, João, só para as pessoas entenderem. É que no paper do Wiseman, depois eles provam que tem a unicidade de 3 vezes em diante. Então isso aí, de fato, é o que sobrou só. A unicidade deles também vai para o longo alcance. Então esse é o que está faltando mesmo. No 3 meses, eu não me lembro. 3 meses tem unicidade também? 3 meses?
Não.
Ah, 3 meses não.
Não, crítico não sabe. To the critical value? I don't think so. I don't think so.
I think yes. I think that in some presentation of someone,
Really?
that they got the 3 over.
Ah.
Yeah, because they had also papers for maybe things can say something. No? No, but this is no. This is another constraint. No, this
Yeah.
is for the yes. Log 3 of log 3 is for the
For the initial value here,
yeah.
the start of the. Oh no, this is just future work, something that could be done. Yes.
Yeah, the temperature which improves phase transition. What is the dependence?
With E, this is actually, I think they are not. Yes, I'm not sure that they are not related because. Yes, but what you do is something like this. You show that actually the mu plus in the lambda of seeing this. This is smaller than E to some constant e to the minus beta here. And you have another constant here that comes from the probability that is E to the constant E squared. So you see, these two things are yeah, the dimension comes because we can only do this estimation for the dimension 2. But the dimension should be hidden in this constant.
For long range?
Yes, for long range. Yeah. No, for the short range, they can actually get to the critical temperature. Is this paper? Let me see if it is here. Yes, it's a quite recent result, last year. So that they show that, okay, what they show is that you take a temperature that is strictly smaller than the critical temperature of the easy model. So there is a weak enough. No external field, yes. No. Yes, yes.
But I guess, I mean, so if I understand the question, so there is a critical temperature for the random field.
Yes.
But that's not supposed to be the same as the critical temperature.
It is supposed to be the same in the sense that think of this: you take a temperature, you take the using model, right? And you take a temperature that you have phase transition. It is to be expected that if you add the random field, if your variance is very, very small, then for this fixed temperature, it should not make any difference. And that's actually what they prove in this paper. This is actually what they prove. Yes. Yes. Oh.
Once the energy, I mean, it's about Roman behavior where we're trying to kind of control the difference like activities and power. But if you consider alpha to be equal to 1, and you try to follow the contour characteristics.
Yes.
You have to add this energy of the interior contour like f of interior. Like, is that the problem? Or really
No. This is only a problem. You need that extra fat only if you're trying to do things in 2 dimensions. In G or plus dimensions, if you can bound, as long as you can bound your energy by something like the difference of the energy by the size of the contour. Yes. So as long as you have something like this, then in high dimensions you are okay. Actually, that's a very good question because you can show that. Okay, try to do the same thing but in 2 dimensions. Ding has a paper where he shows that if you look at this bad event here, okay, if you take this bad event here, then this is actually consider you are looking at contours inside a box. So this probability grows with the box. So there is no hope of extending these sort of things when you have a control like this. In dimension 2. In dimension 2. Yes. Yes, the F should matter.
Dimensional equation 3, you already have the short. So it's second dimension 4.
Yeah.
More. Yes, I mean, the limit is we make a reservation for 7, but of course you can 7. So, 7? No. 50. 7 pounds. For 7. No, the time. No, much more than the year. No, but I think that you could go early if you want to take track ideas and other things. Yes, I sent that in the mail. It's in the reposted. It's very close from the. I think it's close. I think it's Oscar Freire. It's close to Oscar Freire. It's close. Yes, it's close. Not so. It's close from this. The Nick Shaman also in the. There's the very giant McDonald's, but don't go there. Go to the barbecue. And, yeah, it's close to Oscar Freire. But I sent the size address in the mail. So just ask for the Uber, okay, go movidos, remotos, e we go to numbers. Okay, so this was okay.